Hello and welcome to the first module of this course, Self-Driving Car. Now that you have PyTorch and Kivy installed on your system, we are ready to start implementing the self-driving car, and I can tell you we have an exciting adventure ahead of us. So the first thing we're going to do now before we start is set the right folder as working directory. That's very important because we are going to have 3 files to implement this car, and all the cars are connected to each other. So when you execute a file, it will take the classes, functions, and objects from another file, and this other file has to be in the same working directory as the file that you're executing. That's why it's very important to have one same folder with all the files, and that is your working directory folder. So let's just get this done, and then we will be able to start. So first thing you do is go to File Explorer here. That's this window, and then you will probably be on your desktop. So right now, as you can see, I'm on my desktop, or maybe you'll be in your documents. But anyway, you have to find the folder that contains your artificial intelligence A to Z template folder that you downloaded from the SDS website that Kirill walked you through. So just find this folder, then open it from File Explorer, then go to Module 1, Self-Driving Car, and then there you go. This Module 1 Self-Driving Car folder contains 3 files. That's the 3 files that are connected to each other to implement not only the self-driving car on the map, but also the brain of the car, that is the AI that will be integrated to the car. And so this folder containing these 3 files is your working directory folder. And now to make sure that this folder is set as working directory, you can click on the tool button here and then restart kernel. Then you can click on yes, and there you go. Now you are sure 100% that this folder containing your 3 files is set as working directory. Okay, and so now before we start, I would just like to explain quickly what are these 3 files. So as you probably recognized, the first one here, ai.py, is the file that contains the brain of the car. So that's in this file that we will implement the artificial intelligence that will be integrated to the car. So that's why I'm calling it the brain of the car, because this artificial intelligence is based on a neural network. So it will be like the car will have a neural network inside of it. That's why I like to call it brain. Then the second file here is a Kivy file, car.kv. And you cannot open it here in Spider, but you can open it from a text editor. And actually that's what I'm going to do right now. I'm opening it with Sublime Text. There we go. That is Sublime Text. And this is this car.kv file opens in Sublime Text. For those of you who are on Windows, you can open it with Notepad++. So here is what the Kivy code looks like. We're not going to focus on it in this course because this is only related to Kivy, but basically to understand what's going on here, well, as you can see, we create several objects that will be on the map. So for example, this first object here is the car, and for this car you can define some variables like the angle, that is the angle of rotation. Then you can define the shape that you want your car to have. So it will be a rectangle, like the basic shape of a car. Then you have some other objects, ball 1, ball 2, and ball 3. So these 3 balls here will be, as you will see later, the sensors of the car, because the car will have sensors that will detect if there is some obstacles around the car. So these 3 balls here are just to highlight the sensors on the car. So we will see them, and besides, I set a different color for each of them. And then we have a last object, which is to connect all the previous objects together to make the car, because the sensors will be attached to the car so that when the car moves, well, the sensor moves as well. Alright, but this is not the most important here, so we're gonna move on to Python. This is just to show you what Kivy looks like, and this file, of course, will be connected to our other files, and mostly it will be connected to the third file, map.py, which is this one right here. And map.py, what is it? Well, this is where we make the whole map, and also the whole game, because you will see that we will be playing some games with the car. We will give it some challenges, like avoiding some obstacles or doing some round trips between 2 destinations on a more and more difficult road. So we will make a game, and that game happens in this big file here. So this file is important, therefore we're going to see it in details. However, since this is not directly related to AI, we will not code it line by line. I will just explain each line of code. Besides, in the template folder, you'll find the same code as this one, but commented. So each line of code will be commented, so that if you're interested in knowing how to develop a game within a Kivy application, well, you will be able to understand everything that we do here. But what's important also is that not only we make the map in the game, but also we make some important connections between the map and the future AI that we will implement afterwards. And by the way, this is much more important, and therefore we will implement it step by step. We will write together each of these lines of code. But for the map, I will just describe all the code sections here, and that's what I will do in the next section, right after this tutorial. I think the next two tutorials are important for you to understand the connection between the map and the AI. Alright, so I will be explaining all this in the next tutorial, and until then, enjoy AI! Hello and welcome again to our self-driving car module. So in this tutorial I'm going to explain the environment on which we will implement our artificial intelligence, and that will contain of course the car that we will train to drive itself and to avoid obstacles, and on which we will draw some roads and some blocks for our car to navigate around them. So we will later build this artificial intelligence to train this car to drive on the road, without crossing the limits and avoiding some obstacles that we will put inside the road. So this is a pretty exciting challenge, and actually there are two separate files, as you can see. There is the AI Python file, that's our artificial intelligence that will do all the training to train the car how to self-drive, and we have the map.py file, that is the code that makes all this environment. So here is that code. That's actually 200 lines of code, a little more. So this code is not typically related to AI. It is just the code to make the environment, to make the map. So I'm going to go through each of the sections one by one to explain, but we're not going to implement this code line by line from scratch because we want to focus on artificial intelligence. But let's still go through the sections one by one to understand what's happening. So first, we import the essential libraries. That's for any code. We need some libraries to perform some tasks more efficiently. Then we import all the Kivy packages. So that's not very important because this is all specific to Kivy. We're using Kivy to make the map, and so we're importing a lot of classes and objects to be able to make this map and add some tools in the map. Alright, then this line is important. This line is AI related, because basically this is where we import our brain, the brain of the car, which will be an object of this DQN class, and the DQN class is our artificial intelligence itself. You will see we will implement the DQN class in the following tutorials, and as you might have guessed, DQN stands for Deep Q Networks. So we will implement a Deep Q learning network, and then once it's ready, we will be importing it here with this line from the AI. And the AI is, of course, our AI Python file. Alright, so can't wait to implement this. This is going to be quite a journey, but you will see this is going to be very exciting, because thanks to the AI, the car will be able to drive itself. Alright, and now, before I move on to the next sections, we have to explain how we will train this car. I'm not going to explain the neural network right now, but I'm going to explain the idea of how we're going to train the car to drive itself and to avoid obstacles. So in real life, if you want to train a real car to avoid some walls or some obstacles, well, what would you do? You would definitely not take real walls or real big obstacles and smash your car onto them. That would cost you a lot of money. Instead, a more intelligent idea would be to punish your car not when it smashes a wall or an obstacle, but when it goes onto some sand. So it's like you have a field. This field has some roads on which the car has to stay, and the roads are delimited by some sand. And each time the car goes onto the sand, it's like it's going onto an obstacle, because once the car goes into some sand, it will be slowed down, and we will make sure that the car is penalized, is punished for that. And that is one essential point of our artificial intelligence. The bad reward comes whenever the car goes onto some sand and is slowed down. Alright, and therefore, here I'm introducing last x and last y, which are the coordinates of the last point in memory when we draw some sand on the map. Alright, and then we get our artificial intelligence, which we call brain, and that contains our neural network, and we will call it brain because this is actually the brain of the car, and that contains our neural network. Alright, so in this line of code, as you can see, I'm creating an object of the DQN class. I will remind what classes and objects are, but brain is the object, DQN is the class, and 5, 3, and 0.9 are the inputs of the class. So that's very simple. 5 corresponds to the states that are encoded vectors of 5 dimensions. We will see what they are, perfectly describing what's happening in the environment on the map. Then 3 is the number of actions. There will be 3 possible actions: go left, go straight, or go right. And 0.9 is the gamma parameter in the deep Q-learning algorithm. Alright, and then we have the action to rotation. So action to rotation is a vector of 3 elements, 0, 20, and minus 20. And so we have to do this because the actions are encoded by 3 numbers, 0, 1, and 2, and that corresponds to the indexes of this action to rotation vector. So for example, if the action that is selected at time t is 0, well, 0 corresponds to the index of this action to rotation vector, and the value of index 0 is 0, and therefore we will go straight. Then, if the action selected is 1, well, 1 corresponds to the index of this action to rotation vector, and the value of this vector that has index 1 is 20. So 20 corresponds to a rotation of 20 degrees, and that means the car will go 20 degrees to the right. And then, if the action selected is 2, well, 2 corresponds to the index 2 of this action to rotation vector, and therefore the car will do a rotation of minus 20 degrees, and therefore it will go to the left. Alright, then we introduce the last reward variable, because at each state we will be getting the last reward. So remember, if the car doesn't go onto some sand, then the reward will be positive, and if the car goes onto some sand, well, it will get a bad reward. And at each time, this variable will contain this reward that it gets at each time t. And then we initialize the scores, which is a vector that will contain the rewards, not all of them, but the rewards onto a sliding window, so that we can make a curve of the mean score of the rewards with respect to time. Alright, then in this code section we initialize the map. So we initialize, for example, the send variable. So that's important. The send variable is actually going to be an array in which the cells will be the pixels of the map. And in each cell, we will have a 1 if there is some sand and a 0 if there is no sand. At the beginning, we will not be drawing anything, so there will be no sand at all, and therefore all the cells of the sand array will have a 0, so there will be zeros everywhere. And as soon as we draw some sand, well, the cells on which we draw the sand will get a 1. And we initialize the arrays with all the zeros right here. Sand equals np zeros. Then we have this important thing, which is the goal. So the goal is a point in the map which we will train the car to reach. So it's like a destination. So what is this goal going to be? Well, this is going to be the upper left corner of the map. So we will train the car to go to the upper left corner of the map, and then once it reaches the upper left corner of the map, then we will train it to go to the bottom right corner of the map. So we can imagine the following scenario. The upper left corner of the map is the airport of a city, and the bottom right corner of the map is the downtown of the city, and we will train a taxi or Uber to do some round trips between the airport and the downtown. And of course we will make the task difficult to this taxi by drawing some more and more difficult roads and adding more and more obstacles on the street to see if the taxi can still manage to go from the airport to downtown. So this is going to be fun, and so that's why here I'm setting the coordinates of the first goal, that is the airport, which is at the upper left of the screen. So the map will be like a square like this, and the coordinates of the origin, that is the coordinate 0, 0, is right here. And then larger is this distance here, so the coordinates 20 and larger minus 20 will therefore be right here, the upper left corner of the map. And why did I choose 20 and not 0? Well, that's because we want to train the car not to rush into the walls. We want to train it to avoid the walls as well. And therefore the goal must not be 0 because we don't want the car to touch the wall. We want to touch the goal, so we have to put it right here. And then I'm just introducing the last distance variable, which just gives the current distance from the car to the goal, and that I'm initializing to 0. Alright, and now time to make the car and the game. So we're going to make 2 classes, one class for the car and one class for the game. And inside these classes, we will already make some connections with our AI. So we'll do that in the next tutorial, and until then, enjoy AI! Hello and welcome to this tutorial. In the previous tutorial we initialized the map, and now time for the exciting stuff. We create the car, and we do that with a class, of course. You will see that the class is very practical to create some things that have a lot of properties, because as you can see, not only I'm defining some variables for my car, but also some functions, which of course is the function that will make the car move to the left, to the right, or going straight. So we have a couple of variables that are important to describe the environment. We have, for example, the angle, which is the angle between the x-axis and the axis of the direction of the car. Then we have the rotation, which is its last rotation, which, remember, is either 0 degree, 20 degrees, or minus 20 degrees. Then we have the velocity, the x-coordinate of the velocity vector and the y-coordinate of the velocity vector, and then the vector of coordinates velocity x and velocity y. Then we have the sensors and the signals, and that's very important. The car that we're making will have 3 sensors: sensor 1, sensor 2, and sensor 3. Sensor 1 will be detecting if there is any sand in front of the car. Then sensor 2 is the sensor that will detect if there is any sand at the left of the car. And sensor 3 is the sensor that will detect if there is any sand at the right of the car. And then from these 3 sensors we get the signals. That is the signals received by each of the sensors. So signal 1 is the signal received by sensor 1, signal 2 is the signal received by sensor 2, and signal 3 is the signal received by sensor 3. And so how does it work? Signal 1 is the density of sand around sensor 1, signal 2 is the density of sand around sensor 2, and signal 3 is the density of sand around sensor 3. And how do we compute this density of sand? Well, that's very simple. We take some big squares around each of the sensors. These are actually squares of 200 by 200. And for each of the squares, we divide the number of ones in the square by the total number of cells in the square. That is 20 times 20 equals 400. And that gives us the density of sand because the ones correspond to the sand. We do this for each sensor, and that gives us the density of sand around each sensor, that is, the signals. Alright, so now we have everything to detect the sand, and then we have the move function. And of course the move function is what will allow the car to go to the left, going straight, or going to the right. So let's go through it quickly. We have here the update of the position of the car with its last position, which is self.pos here, and the velocity vector. So thanks to the velocity vector, the position will be updated in the direction of the velocity vector. Then we get the rotation, which we will get further down in the code right here. Rotation equals action to rotation action. Here we will select the action and then getting the rotation. And so this self-rotation equals rotation here is this rotation that we get to know how we need to rotate the car that is going to the left or to the right. Then we update the angle, which I remind is the angle between the x-axis and the axis of the direction of the car. And then once the car has moved, then we have to update the sensors and the signal. Because of course, when the car has just rotated, well, the sensors have rotated as well, and therefore we need to rotate them by using the rotate function, and to which we add the new position. And why do we have this vector of 30, 0? Well, that's simply because 30 is the distance between the car and the sensor. You know, it is the distance between the car and what the car detects. And then, once the sensors are updated, well, then it's time to update the signals. And so here we do exactly what I explained to compute the signals. We get the x-coordinate of our sensor, then we take all the cells from -10 to +10. Then we do the same for the y-coordinate, taking all the cells from -10 to +10. So therefore we get the square of 20 by 20 pixels surrounding the sensor. And inside this square, we sum all the ones. So basically we sum all the cells because the cells contain either 0 or 1. And since in a 20 by 20 square there is 20 times 20 equals 400 cells, well, we divide it by 400 to get the density of ones inside the square. And that's how we get the signal of the density of sand around the sensor. And we do the same for the second sensor and the third sensor to get the second signal and the third signal. Okay, so that's to detect the sand. And then the 3 lines of code here are very important. it's another bad reward that we want to give to our car when it is reaching one of the edges of the map. You know, we don't want the car to rush into some walls, and therefore we want to penalize it, to punish it when it's getting too close to a wall. And therefore that's what we do here. If the first sensor is larger than longer minus 10, that is larger than here, because longer is this distance here, so longer minus 10 is right here. So if sensor 1x larger than longer minus 10 concerns all the points that are here, that is if the car is getting closer to the right edge of the map, or if self sensor 1x lower than 10, so that's right here if the car is getting closer to the left edge of the map, or if sensor y is larger than larger minus 10, that's the upper edge of the map, and or if self sensor y is lower than 10, that is the lower edge of the map. And so if the sensor 1 is reaching any of these four edges, well, we will put the signal of the sensor, signal 1 is the signal of sensor 1, we will set it to be 1. And what does that mean? That means full send, like a full density of send. It's like the worst send you could get. There is so much send that it's going to stop your car. So signal will be 1, and therefore the car will get a terribly bad reward. Alright, and then we do the same for signal 2 and signal 3 from sensor 2 and sensor 3. Alright, and then we create the game class. So that's basically the class to create the game, because so far we have only created the car, and now of course we have to create the map. We have to create the game itself. So we will not be playing the game, it's our AI that will be playing the game, and the game is actually to avoid the obstacles and to go from the airport to downtown and vice versa. So in this game class we need to create some objects like the car, then we need to define the update function. That is the most important, and actually we will focus on that right now, because that's in this update function that we will select the action that the car has to do at each time to accomplish its goal. And this action is exactly the output of our neural network. The neural network that will be at the heart of our artificial intelligence. And so this action is returned by the brain of the car, which I remind is the object of our DQN class that we'll be making in our AI file. And this object has a method that is called update, and it takes as input the last reward and the last signal. So the last reward is of course the last reward obtained by the car, and the last signal is of course the last signal of the three sensors. Signal 1 from sensor 1, signal 2 from sensor 2, signal 3 from sensor 3. But then I'm adding two other inputs, which is the orientation of the car with respect to the goal. So for example, if the car is heading towards the goal, then the orientation will be equal to 0. If it goes slightly to the right, then the orientation will be close to 45 degrees. And if it goes slightly to the left, the orientation will be close to minus 45 degrees. So that's the fourth input of our input state. And then there's a last input, which is minus orientation. So usually the inputs of a neural network are independent. There is no multicollinearity, but it doesn't really matter if we add this, because the neural network will just fix that with the weights. But still, I noticed that by adding this minus orientation, well, that allows the car, the training of the car, to stabilize the exploration. You know, we're doing this so that the AI doesn't always explore in the same direction. By adding this minus orientation, we make sure that it explores in both directions, right or left. And so this, the three signals plus the orientation and minus orientation, are the 5 inputs of our encoded vector, which will go into the network. That's our input vector that will go into the network. And after it goes into the network, well, the network returns the output, which is the action to play at each time. And the output is returned by this update function that contains the network itself and the outputs of the network. And therefore, that's why we have to input the last signal, that is the input state, and also the last reward, because the action to play also depends on the last reward. Alright, and then we update the mean score of the rewards, we update the rotation, we use the move function to rotate the car according to the action that was selected, we update the distance of the car to the goal, and we update the positions of the sensors. Ball 1, ball 2, and ball 3 corresponds to the balls that will represent the sensors on the map. You will see that very quickly. And then here, that part is very important, because that's where we penalize the car if it goes onto some sand. Because as you can see, this means if the car is onto some sand, well, it will be slowed down. So that's where we reduce its velocity. You know, its velocity is usually 6, as you can see here. And if it goes onto some sand, it will be 1. So it will be slowed down to 1. You'll see how the car will be slowed down once it goes onto some sand. So it is slowed down, and besides, it gets a bad reward. It gets a -1 reward. And that's actually the worst reward you could get. The best reward is 1, the worst reward is -1, and the reward is between -1 and +1. And then otherwise, if the car isn't onto some sand, well, it keeps its usual speed of 6, and then we add something else. If it's getting closer to the goal, then it will get a slightly positive reward. And if it's getting further away from the goal, well, it gets a slightly negative reward, -0.2. And then last conditions that are related to the reward, well, that's if the car is getting too close to one of the edges, as we spoke of earlier. Remember when we talked about full sand? Well, if the car is getting too close to the left edge of the map, it gets -1 reward. If it gets too close to the right edge of the map, it gets reward -1. And if it gets too close to the bottom edge of the map, it gets reward -1. And if it gets too close to the upper left of the map, it gets rewards -1. So that's a terrible punishment. And so you will see how it will learn fast not to rush into some walls. Alright, and then this is to update the goal when the goal is reached. So, you know, when the car reaches the airport, which is the first goal, that is the upper left corner of the map, well, the goal changes to the bottom right corner of the map, which is downtown. And that's exactly what we do here. We update the x coordinate of the goal and the y coordinate of the goal. And then we update the distance from the car to the goal. Alright, and then that's less important. That's just a class that will add the painting tools, you know, for us to be able to paint some roads or some obstacles on the map. So that's more related to Kyvie. You can have a look if you want. I'll provide the commented version of this code, and I'll provide some reference if you want to go deeper on how to do that with Kyvie. But we're getting further from artificial intelligence, so I'm not going to go into the details of it. And that's the same for the last code section here with the car app class. That is just to add the API buttons, clear, save, and load. So that's what we do here, clear canvas, save, and that's actually very important. That's for us to be able to save the AI, you know, to save the brain, so that you can reuse it later by taking the load function, which is another tool we add on the map to load the brain of the car, that is to load the memory of the car, how to navigate in the map. And then finally we have the last of the last code section, which runs the whole thing, that is, which runs the map and the AI itself. And actually, that's what we're going to do right now. Let's have a look at everything we make in this code. So right now, the AI is not implemented. So the car will have a very random movement. It will actually look like an insect, but don't worry, we will fix that. Not only we will train it to move like a real car, and train it to navigate, following some roads and avoiding some obstacles. So let's do this. I'm going to select everything and execute. And here is the map, and here is the car. All right, so that little thing here that you see that looks like an insect is our car. So as I told you, the actions are totally random. So at each time, the car selects randomly an action whether to go straight, to the left, or to the right. So that's why it is making some nonsense movements, and that's why it's looking like an insect. So we will fix that, of course. And of course, since the AI is deactivated, well, it is not going to the goal, which is the airport here, or to downtown at the bottom right of the map. And we will fix all this by making the AI. So we will implement the AI into this car or this insect. So you can see the 3 balls here, the yellow one, the red one, and the white one. That's our 3 sensors. So that's what will detect if there is some sand around it. And speaking of sand, well, let's draw some. So to do so, I just need to do a click left here and, you know, drawing some sand by still clicking left. So right now I'm adding some sand. We can add some more. So each time I'm adding sand, as you can see, that's putting 1s in the sand array. That's the sand array. That's the 0, 0 coordinates of the origin. and here there are a lot of ones. And as you can see, well, that's good to see, the car just went onto the sand and was slowed down. So as you can see right now, it is really slowed down because it's going onto the sand, and right now it's trying to escape. And so, what we'll do is we will draw some roads, and we will draw some roads from the airport to downtown, and we will train the car to stay in the road and to avoid the obstacles. All right, and as you can see, there is the clear button to clear the sand. There is the save button to save the brain of the car. And actually there is the score curve that we spoke of. So that saves the AI, that saves your model actually, the brain of your car. And then you can, when you leave your code or turn off your computer and you want to go back to it again, you can use the load button to load your model, that is to load the brain, and that will get the trained AI of your car. All right, so now I can't wait to start making the AI. This will be a lot of fun. We will make our neural network and we will punish the car as soon as it doesn't do what we want. So let's do that from the next tutorial, and until then, enjoy AI. Hello and welcome to this tutorial. Alright, so now we are going to implement our artificial intelligence from scratch. We're going to code it line by line, and in this first code section we're going to import the libraries. But before we start with this first code section, I would like to explain the connection between the AI and our map.py file. That is, why are we implementing this for the map? What is the purpose of our AI and where will we be using it? So it's actually very simple. We're only making our AI to select the right action at each time. So okay, we import the DQN class from our AI file, so we will be making this DQN class in this file, but then we import it only to select the right action to play at each time. And we select this action exactly at this line. Action equals brain update, last reward, last signal. Last signal will be the input of the neural network. It's composed of the 3 signals of the sensors plus the orientation and minus orientation. So that's the input, but then the output is the action to play, and that's only what we'll be taking from our AI file that we're about to make. So keep that in mind, it's very simple. We first import the DQN class from the AI, then we create the object brain from the DQN class, which takes as input the encoded vectors for the states of 5 dimensions, the 3 signals plus orientation plus minus orientation, the 3 actions go left, go straight, or go right, and then this gamma parameter. That's the only parameters of the DQN class that we will be making. And then, once we create that object, we select in the game class the action to play at each time. And that depends on the last reward and the last signal, which is the input. And that's all. That's the only purpose of making this AI. That's in order to have a real artificial intelligence playing the right actions at each time, the right move, instead of having random actions like we observed in the previous tutorial. Alright, so let's do this. Let's implement our artificial intelligence. And as we said, we're going to start by importing all the libraries that we'll be using to implement it. So that way we will have all the tools we need. Alright, so let's start with the first one. The first one is the inevitable, the Numpy library. The Numpy library, I always recommend to import it. It's the library which allows us to play and work with the arrays. And this NP here is just a shortcut, more convenient when we want to use NumPy. Alright, then the second library is random. So this is just because we will be taking some random samples from the different batches when implementing experience replay. So we have to import this random library as well. Then we will import OS. That will be just useful when we want to load the model, because once the model is ready, we will implement some code to save the model, and then another code to load the model. That's when we want to, save the brain and load the brain, whenever you want to shut down your computer and reuse the brain that was trained before for some new experiment. So that's important. Then we are going to import the Torch library, essential. That's because we will be implementing our neural network with PyTorch, which I recommend much more than the other ones for artificial intelligence because it can handle dynamic graphs. So there we go with Torch. Then from Torch, we are going to import torch.nn. The NN module is the most essential one. That's the module that contains all the tools to implement some neural networks. And of course, there will be a deep neural network that will take as inputs the 3 signals of the 3 sensors plus orientation and minus orientation, and will return as output the action to play. Well, actually, it will return the Q values of the different actions, and using a softmax, we will return the action to play, only one, the most relevant one to accomplish the car's goal. So torch.nn, most essential one. Then we're going to give a shortcut to the functional package from, here we go, the functional package from the NN module. So this functional package contains the different functions that we use when implementing a neural network. So typically the loss function, we will be using the uber loss because that improves convergence, and the uber loss is contained in this functional submodule from the NN module. And since all this is pretty long, we're going to give it a shortcut and we're going to call it F, simply. Then only 3 modules to import left. So the next one is another essential one, which is optim, and we take it from still the torch library and then optim. There we go. And let's just call it optim instead of torch.optim. So that's of course for the optimizer. We will be importing some optimizers to perform stochastic gradient descent. So we will definitely need it. And then we need to import autograd, and that's only to take the variable class from autograd. So the purpose of it is a little bit technical. Basically, we need to import the variable class to make some conversion from tensors, which are like more advanced arrays, to a variable that contains a gradient. So it's like we don't want to have only a tensor by itself. We want to put the tensor into a variable that will also contain a gradient. And to do this, we need to use the variable class to convert this tensor into a variable containing the tensor and the gradient. So that's a little bit technical, but that's what we have to do when working with PyTorch. And we do this thanks to the variable class. But before getting the variable class, we need to import torch.autograd. And let's give a shortcut as well, autograd. And then from torch.autograd, we import variable. There we go. And now we have all the libraries that we'll be using to implement our AI. So we won't bother importing any other library. We have all the tools we need, and now we're ready to create the architecture of the neural network. So that's exactly what we'll do in the next tutorial. And until then, enjoy AI. Hello and welcome to this Python tutorial. Alright, so we have very exciting tutorials ahead of us. We are going to start by creating the architecture of the neural network. That is, we will make the neural network that will be at the heart of our AI and that will return the action to play at each time t. So let's do this. So since we want our neural network to be an object, we're going to make a class, and that's because it's much more convenient. You know, a class is the model of something we want to build. We want to build a neural network, and we need to make some kind of instructions which will all be contained in a class. And in this class, we're going to make 2 functions. First, the init function, which is the function that comes up all the time when making a class, and that basically defines the variable of your object, that is the neural network. You know, the variables attached to the object as opposed to the global variables. And so this is in this init function that will define the architecture of the neural network. You know, defining the input layer, which will be composed of 5 input neurons because we have 5 dimensions for the encoded vector of input state. Then we will define some hidden layers. Maybe we'll start with 1 hidden layer, and then you will be welcome to try some other architectures of the neural network. And then of course we will end up with the output layer that will contain the possible actions that we can play at each time. So that's exactly what we'll do in this init function. And then we will make another function still inside the class, which will be the forward function, and that will be the function that will activate the neurons in the neural network, you know, that will activate the signals. And so we will use a rectifier activation function because of course we're dealing with a purely nonlinear problem, and this rectifier function breaks the linearity. But mostly we're making this forward function to return the Q values, which are the outputs of the neural network, but we have one Q value for each action, and later on we will be returning the final action by either taking the max of the Q values or using a softmax method. We will see that afterwards. So in this tutorial we're going to start by implementing the init function, and in the next one we will be implementing the forward function. So let's do this. First we need to introduce our class. So we start with class, then we give a name to our class, which is, well, we can call it network. And then in this network class, I'm going to use an object programming technique, which is called inheritance. And that is just to inherit from all the tools of a parent class. So our network class that we're about to make is a child class of a larger class, which is nn.module. So that's just to inherit from all the tools of this module class, which are of course the tools to implement a neural network. So that's a very powerful and efficient trick in object-oriented programming. That's called inheritance, and right now we are inheriting from this module parent class. All right, and now we're ready to go inside the class. So I'm pressing enter, twice actually, because we'll be making two functions, and we're starting with the init function. So the init function, we have to name it this way with two underscores, then init, and then again two underscores. That's just Python syntax. That is just how we have to do it. And then we need to input the arguments. So we have three arguments. The first one is a compulsory argument. That is actually self. And self, there is no mystery about it, that refers to the object that will be created from this class that we're about to make. You know, we're making this class. It's like some instructions, some model of this neural network we want to build. And then once the class is ready, we can make as many neural networks as we want. And each of these neural networks will be some object of this class. And since we'll be using the object for some other purposes, we need to spot what are the variables of the object. And to spot this, we are using this self here to specify that we're referring to the object. So whenever I want to use a variable from my object, I will use self before the variable to specify that this is a variable of the object. All right, so that's the first argument. And then we have two other arguments, which are of course the number of input neurons and the number of output neurons. So the number of input neurons, we're going to call it input size. And that's actually 5, because our input vectors have 5 dimensions, the 3 signals, plus orientation, plus minus orientation. That's our vectors of encoded values that describe one state of the environment. These 5 values are enough to describe a state of the environment. We could have thought of less values or more values, but that's what I tried, and it actually makes sense because we actually need one signal from the left, one in front of us, and one at the right. You know, when we're driving a car. We could have gone for a 360 signal, you know, like the signals at the top of the Google cars, but we can totally self-drive with 3 sensors. And then we have this orientation and minus orientation to, you know, keep track of the goal that we're trying to reach. And then we have, of course, the output neurons of our neural network, which correspond to the actions, and we have 3 possible actions, going left, going straight, or going right, and therefore I'm going to call it NB action, and there will be 3 of them. Alright, but so far we only have to give names to the inputs, and then we'll use these variables to do the computations inside the neural network. Alright, then I'm going to start by using another PyTorch trick. This trick is the super function. That's a function that actually inherits from the NN module, so that's why we had to use inheritance to inherit of the module tool. This is the first tool we use. And so basically, we're only using this super trick, this super function, to be able to use the tools of module. So that's much more efficient. And inside this super function, I just need to specify first the network. So that's our network child class, you know, because this is inheriting from the module parent class, and then our object. And then I'm just adding dot and our init function, like this, exactly how we named it. All right, so that's just a trick. That's just to use all the tools of nn.module. Then we can move on to the next step, which is to specify the input layer. So basically what I have to do is introduce a new variable that will be attached to the object, And this variable will contain the number of input neurons. So not to be confused with input size is the argument of the init function, but that's not the variable that is attached to the object yet. The variable that is attached to the object, well, as I just mentioned, we need to specify that it is instead attached to the object, so we use a self dot, and now we give a name to this first variable attached to the object. And so we can simply give the same name as the input, we can call it input size, and we will say it is equal to the argument of the init function, that is input size. Alright, so each time I'm creating an object from the network class and I'm specifying the input size, like for example I'm inputting 5, there will be a 5 here, and therefore the input size variable of our object will have the value of 5, because this input size here will be 5. And therefore our neural network will have 5 input neurons in the input layer. Alright, and then that's the same for the other variable that we want to attach to our object, and as you might have guessed, this is going to be a variable for the number of output neurons. And so same, we take our object, self, and then we give a name to this second variable of the object. We're going to call it nb action, and this will be equal to this argument here giving the number of actions, that is the number of output neurons, and so we set it equal to nb action. So actually nb action will be equal to 3, therefore the variable nb action attached to our object, to our network, will get the value of 3. Actually we can see a warning here, it says undefined name nn. Well, that's because here we use the nn shortcut, and we need to use the shortcut here nn for our torch.nn module, and then it will disappear. Here we go, perfect. Right now we have no warnings. All the warnings here are just to specify that what we import is not yet used, but that's okay, we will be using them afterwards. Alright, then we have another 2 variables we want to define for our object, and this will be the full connections. The full connections between the different layers of our neural network. So since right now we want to make a neural network composed of only one hidden layer, well, there will be 2 full connections. There will be one first full connection between the input layer and the hidden layer, and one second full connection between the hidden layer and the output layer. So let's start with the first full connection. We're going to call it fc1, and again I use self here to specify that fc1 is a variable of my object. So self.fc1, which will be equal to, and now we use the nn module, and we're going to use a function called linear, and that's exactly to make this full connection between the neurons of the input layer to the neurons of the hidden layer. And what do I mean by full connection? That means that all the neurons of the input layer will all be connected to all the neurons of the hidden layer. And so to make this full connection, we use this linear function, to which we need to input some argument. And as you can see, these arguments are in features, so that is the number of neurons of the first layer we want to connect, then the out features, that is the number of neurons of the second layer we want to connect, that is the layer at the right, that is the hidden layer, and bias equals true. So bias equals true, we will keep the default value. That's in order to have a bias, and not only some weights attached to the neurons, we'll have the weight and one bias for each layer. And so, well, let's see what we need to input. So the first argument in features is the number of input neurons in the input layer. And so what is it? Well, that's actually input size. That's the argument of our init function, which later will be equal to 5, the 3 signals, orientation and minus orientation. So here we go. We input the first argument, input size, and then the second argument is out features, that is the number of neurons we want to have in the second layer that will be fully connected to the first layer. And so now the question is, how many neurons do we want in this hidden layer? Well, I did a lot of parameter tuning, I did a lot of experimenting. That's what we do in AI, or that's what we do in deep learning in general. We do a lot of experimenting to see what would be the best neural network for our specific problem. And so I tried many values, and I ended up choosing 30 neurons in a hidden layer, and you will see that with this number we will get some pretty good results. But then feel free to change the architecture of the neural network, feel free to play with it, you can not only change the number of hidden neurons in the hidden layer, but also you can add some more layers so that maybe you get an even better car. But 30 hidden neurons will get us a good neural network and a good car. So that's what we go for, and there we go, we have our first full connection ready. With this linear function, we make the full connection between the input layer and the hidden layer. And now, time to make the second full connection, that is the full connection between the hidden layer and the output layer. So there we go. We're going to call this second full connection FC2. There we go. And still this is a variable from our object, so I'm using self here. And then again we use, well, actually we can copy this because we're going to use the NN module and then the linear function. But then we need to change the arguments, of course. First, that's the same. First is the number of neurons we want to have in the first layer of the full connection. So that's the hidden layer, and therefore that is 30. And then second argument is the number of neurons in the second layer of the full connection, and that corresponds to the output layer, and the output layer has NB action neurons, which later will be 3, because we have 3 possible actions. But so far, we have to use the names we defined, that is the names of the argument of the init function, and therefore we input here NB action. And there we go. First of all, our 2 full connections is ready, and second of all, our init function is ready. So that's what will initialize our object whenever we create an object from the network class. And so as soon as we create an object, well, all these variables, the 4 variables here, input size, NB action, FC1 and FC2, will be defined, and that's how we'll get the architecture of our neural network for each object that we create. Each object will correspond to a neural network of 5 input neurons, 30 hidden neurons, and 3 output neurons. So there we go. We are done with this first init function, and now we can move on to the second function, which is the forward function, and that will be used to activate the neurons in the neural network using the rectifier activation function, and mostly to eventually return the Q values, which are the outputs of our neural network. So I can't wait to do this in the next tutorial, and until then, enjoy AI. Hello and welcome to this Python tutorial. Alright, so we just built the architecture of our neural network with the init function of our network class, and now we're going to make a second function, which is going to be the forward function, and that's the function that will activate the neurons. That is, it's the function that will perform forward propagation. So let's do this. Let's make this function. Let's call it forward, as we just said, and this function is going to take 2 arguments. First is, as usual, self, to be able to use the variables of the object, because we're going to use FC1 and FC2. So we need this self to be able to use these variables. And then we're going to need a second argument, which is our input. And we're going to call it state, because state is exactly the input of our neural networks. That's the states that are the inputs entering the neural network. And then as output, we will have the Q values of the 3 possible actions, go left, go straight, or go right. But we don't need to input it as an argument here because that's exactly what we want to return. So this forward function is not only going to activate the neurons, but also and mostly it will return the Q values for each possible action, depending on the input state here. Alright, so that's the 2 arguments we need. And now let's go inside the function and let's specify what we want it to do. Okay, so the first thing we're going to do is activate the hidden neurons. And we're going to call the hidden neurons by the variable x. So x represents the hidden neurons. And so how are we going to activate them? Well, of course, we're going to take our input neurons. We're going to use our first full connection FC1 to get the hidden neurons. And then we're going to apply an activation function on them, which will be the rectifier function. So how are we going to do that? Remember, we imported the torch.init.functional module that contains all the functions in PyTorch to implement a neural network, and we gave it the shortcut F. So actually what we're going to do now is we're going to use one of these functions from the functional module, and this function is the Relu function. So what is Relu? Relu is the rectifier function that you saw in the intuition lectures. That's just the name given to the rectifier function. But since this function is taken from nn.functional, which was given the shortcut F, we need to type here first F, dot, and then that's where we can take this function. And actually, if I type RE, here we go, we have the Relu function. So that's the rectifier function that will activate the hidden neurons, that is X. So in this Relu function, now we understand perfectly what we have to input. That's the neurons that we want to activate, that is the hidden neurons. And so to get these hidden neurons, we're going to take our first full connection FC1, which we will apply to our input neurons to go from the input neurons to the hidden neurons. So let's take our first full connection FC1, but our first full connection is a variable of our object. Therefore, we need to type here first self.fc1. Here we go. That's the first full connection of our neural network. And inside this first full connection, we're going to input our input states to go from the input neurons to the hidden neurons. And so since we gave it the name state, well, here we have to input state. And there we go. We now get activated hidden neurons. All right, and now that we have the hidden neurons, we are going to return the output neurons. So next line, and as you understood, the output neurons correspond to our actions, but these are not the actions directly. These are the Q values, because we're building a deep Q learning model that combines a deep learning model to Q learning, and therefore we use Q learning here to get the Q values for each of our actions. And then later, using a softmax or an argmax, we will get the final action. So here, the variable I'm about to introduce will correspond to the output neurons. And since the output neurons are the Q values, well, I'm going to call this variable Q values. There we go. So Q values. And now we directly take our full connection, which is the variable fc2, but a variable from our object. So we take here self.fc2. And of course, here we input the neurons of the left side of this full connection. That is what we got from the first line, which is X. So X, there we go. We now get our Q values. That's the output neurons of our neural network. Okay? And then last line of code, of course, this forward function is used to return these Q values. So we just have to add a return and simply Q values. And that will return the Q values for each possible action: go left, go straight, or go right. All right, so congratulations, we're done with our first class, and actually we're done making the architecture of the neural network. Remember, this is not a finished job. You can always improve the architecture of the neural network by trying different ones. So feel free to do that by adding more neurons here. For example, if you want to add 50 hidden neurons, you can just replace the 30 here and the 30 here by 50. 50 and 50. And then you can add some more hidden layers by making some new full connections. Well, that's really the job of an artist. There is no general rule of what would be the best architecture in each situation, so that's why we have to experiment. But let's already try with that. You will see that we will get eventually a pretty good self-driving car. Alright, and now we're going to make the next class, which is about experience replay, and we will be making that in the next 3 tutorials. Until then, enjoy AI! Hello and welcome to this Python tutorial. Alright, so in this new code section, we are going to implement experience replay. So we're going to make a new class, which we will call replay memory, and that will implement experience replay exactly as you saw in the intuition lectures. But first, let's give a quick reminder about what is experience replay. So, you know, all this artificial intelligence is based on Markov decision processes, and Markov decision processes consist of looking at a series of events. So the events are, you know, for example, going from one state st to the next state st plus 1. But if the events were like that, well, since the next state is very correlated to the current state, well, the network would not be learning very well. So for those coming from the deep learning course, that's exactly the same as where we learned our time series with only one time step. It was not learning anything because one time step was not sufficient enough for a model to learn to understand long-term correlations. So that's the same here, and that's why we have to implement experience replay. So how does it work? Well, that's very simple. Instead of only considering the current state, that is only one state at time t, we're going to consider more in the past, so exactly like for our LSTMs, and therefore our series of events will not be st and st plus 1. This will be, for example, the 100 states in the past, So st-100, st-99, up to st-1, and then st. So in other words, we put the 100 last transitions into what we call the memory. And that way we have a long-term memory as opposed to a short-term memory, or even should I say, an instant memory. And that makes the whole deep Q-learning process work much better. And then, once we create this memory of the last 100 events, we will sample, that is, we will take some random batches of these transitions to make our next update, that is, our next move, by selecting the next action. And therefore, in this replay memory class that we're implementing for experience replay, we will make three functions. First of all, the init function. As usual, that's the case for any class. And so in this init function, we will define the variables that will be attached to the future instances of the class, that is the future objects that will be created from this class. And so very simply, these variables will be the memory of the 100 transitions, the 100 events, and the capacity, that is the 100 number. You will be welcome to try a longer memory by increasing the capacity. So that's the first function, init function. And then we'll make two other functions. One push function to make sure that the memory doesn't ever contain more than 100 transitions. And for this, we'll use the capacity by just doing one simple if condition. And then eventually, we will make the sample function, and that will be, of course, to sample some transitions in this memory of the last 100 transitions. All right, so let's start by introducing the class. So as usual, we start with class, and then we give a name to the class. So we call it replay memory. And then in parentheses, we input object. Then colon, and then here we go, we start with the first function, the init function. So that's exactly the same as before. We start with def, then 2 underscores, init, 2 underscores again, and then the variables. So there is of course self, which is the variable attached to the future instances of the class, the future objects. And then we're gonna have another variable for you to be able to try some other experience replay, some other memories. And that's going to be the capacity. So this capacity will simply be the number 100 because we're going to make experience replay with the 100 last transitions. All right, and then colon, and here we go. Let's go inside the function and let's define the variables of our replay memory objects. So the first one will be self.capacity. And as you probably understood, this will be the capacity, that is the maximum number of transitions we want to have in our memory of events. And this will be equal to the argument we will input when creating an object of the replay memory class, and therefore that is capacity. That's the argument of the init function. So capacity, so again, not to be confused, self.capacity is the name of the variable that is attached to the object, and capacity here is the argument we will input when creating an object of the replay memory class. All right, and then we have a second variable. That's of course the memory. So self.memory. All right, and so what will this memory variable be equal to? Well, this memory is supposed to contain the last 100 events, and therefore this should be a simple list. You know, a list which will contain the last 100 events, the last 100 transitions. And to initialize the list, there is nothing more simple. We just add some brackets like that, and here we go, our memory is initialized. So of course, at the beginning of the experiment, or more precisely the beginning of the exploration, the memory will be an empty list, and then we will put the transitions each time we reach a future state. And speaking of that, that's exactly what we'll do with the next function that we're going to call the push function. We will make this push function to append the events in this memory list, and then we'll use the capacity to make sure that this memory list always contains 100 events and never more. Alright, so let's do this in the next tutorial, and until then, enjoy AI. Hello and welcome to this Python tutorial. Alright, so now we're going to make the push function, which will do two tasks. First, it will append a new transition or a new event in the memory, and then second, it will make sure that the memory has always 100 transitions. I'm saying 100 because we gave the example of 100 events in the previous tutorial, but in fact this will be much more than 100. This will be rather maybe 10,000 or 100,000. We'll see, but anyway, this value will be the capacity. Alright, so let's make this push function. So as usual, we start with def to define a new function, and then we give a name to this function, so we call it push, and this function will have two arguments. First, as usual, self, that refers to the object, and the next one, what do you think that will be? Well, remember, this push function will be used to append a new event in the memory. We already have the memory, so what we need now as a variable is an event. So that will be our argument, our input, and we will append this input in the memory, which is a variable of the object. Alright, so event, you can actually call it event or transition. That's the same. And you will see in the next code sections what exactly is this event, what form it has. Actually, I can tell you now, this event, this transition that we're adding to the memory, is a tuple of 4 elements. The first one is the last state, that is st. The second one is the new state, that is st plus 1. The third one is the last action, that is at, the action that was displayed. And the fourth one is the last reward obtained, that is rt. So that's exactly the form that this event will have. Alright, and that's all. We just need the event because we just want to append the event to the memory, and then making sure that the memory has capacity elements. Alright, so now let's go inside the function. So the first thing we'll do is append the new event to the memory, and that's very simple because we're going to use the append function, so that will be direct. And when we use the append function, we must start with the list to which we want to append something. And this list is, of course, memory. So we start with memory, and since memory is a variable of the object, we start here with self.memory. There we go. So self.memory, and then we add a dot, and then the append function, which is the first one. So append, and inside the append function, we input what we want to append to memory, which is, of course, our event. So event here. And that will append the new event, composed of the last state, new state, last action, and last reward, to the memory. Alright, so that's the first thing done. And then the second thing we need to do is make sure that the memory always contains capacity elements. So let's say capacity is now 100,000. That's probably the capacity we'll choose, because then 1 million elements might make the training slow. So let's say 100,000. Now we're going to make sure that our memory always contains 100,000 transitions, 100,000 events, and never more. So of course, at the beginning, it will have 1, then 2, and 3. But then once it reaches 100,000 events, well, it will always have 100,000 events. So to make sure of it, we simply need to make an if condition with this upper bound that we don't want to go over. So if, okay, so the idea that we'll use here is that if we go over the limit, well, we will delete the first transition, the first event of the memory, and therefore we're going to take the len function to take the length of the memory, that is the number of elements in the memory. So here in the len function we input self.memory, that's the memory. So if the number of elements in self.memory is larger than the capacity, well, in that case, we will remove the first element to make sure that the memory always has the same number of capacity elements. And to delete the first element, there is nothing more simple. We're going to use another function, which is the del Python trick. So del, and therefore we want to remove the first transition, which is the oldest transition in the memory, because the last transitions are the ones that we append, and therefore that's the newest transitions. So the first transitions are the oldest one. And so here we want to delete self.memory and bracket, and we take the first element of the memory, which has index 0. So self.memory 0. Now, interesting, I have a little warning, which says that there is an undefined name capacity. That's because the capacity here is not the input. That must be the capacity variable attached to the object. And therefore here we need to add a self.capacity. And now the warning is gone. So now you understand even more the use of self. That's really to refer to the object, to take the capacity of the object that will be created, that is an instance of the replay memory class. Alright, so we're done with this push function, and so now we can move on to the next function, which is the sample function, which will take some random samples from this memory of the last capacity elements. And doing this will improve a lot the deep Q-learning process. Alright, so let's do this in the next tutorial, and until then, enjoy AI! Hello and welcome to this Python tutorial. Alright, so we have one last function to implement in our replay memory class. That's the sample function, and that's of course to get some random samples from our memory, and therefore this function will return these random samples. Alright, so let's implement it. We are going to call it sample. Here we go, and this function takes two arguments as input. The first one, as usual, self, our future object of the replay memory class, and the second argument is, can you try to guess? Well, we're taking some samples, a fixed size, and therefore we need to choose a size for our samples. And more precisely, we call it a batch size. So that's the name we're going to give to our second argument, batch size. And there we go, we have our two arguments, and now we can implement the sample function. So now I just want to warn you, this is going to get a little technical, but I'll try my best to explain. So we're going to start by creating the samples variable. This is just the variable that will contain the samples of the memory. Alright, so samples equal, and so now how are we going to get these samples? Well, first of all, we have to take our memory, because we're getting these samples from our memory. Then we will probably need the batch size, because the samples we want to get contain batch size elements. So we need memory, we need batch size, and then we need some PyTorch or Python tricks to get the good format of these samples. So what I'm going to do, I'm going to write the line of code, and then I'm going to explain it element by element. So let's do it. I'm starting by taking a zip function. I'm going to explain very soon what it does. And inside this zip function, I'm going to add a star. I'm going to explain that as well. A star and random.sample. So random, as you might have guessed, is the random library that we imported here. So that's the main reason why we had to import this random library. It's because we're taking some random samples. So from this random library, we're going to use the sample function. So this is our variables, and this is a function. So I'm going to add some parentheses. And now, as you can see, sample is a function, and we have to input some arguments. So as you can see, the first argument is self. And actually, speaking of self, this corresponds to self.memory, the memory of our future instance object of our replay memory class. So I'm going to add here self.memory. And then the second argument is, as you might have guessed, the size of the batch we want to take randomly from our memory. And that we gave it a name, that is batch size. So the second argument is going to be batch size. Alright, so the line of code is typed, and now I'm going to explain what it does. So first of all, with this random.sample function, we're taking some random samples from the memory that have a fixed size of batch size. So that's understandable. But then what does this zip star function does? Well, there is no mystery about it. It is just like a reshape function. So for example, I'm going to add a little comment here just to explain, then I'm going to remove it. So let's say that, for example, we have a list of the following elements. For example, first 1, 2, 3, and then the second element 4, 5, 6. So we have a list of two tuples of three elements, 1, 2, 3, and 4, 5, 6. Well then, if I apply the zip function with the star on it, well, what will it become? So zip star list is going to be equal to a new list, but of a different shape. And this different shape is going to be 1, 4, then 2, 3, and then 5, 6. Alright, so that's just what it does. It just reshapes your list. Okay, so now that you understand what this zip star list does, well now let's explain why we have to do it. So, as you understood, we're going to add the events to the memory. And the events have the form, first the state, then the action, and then the reward. But for our algorithm, we don't want this format. We actually want our samples to have the following format: a format composed of 3 samples, 1 sample for the states, 1 sample for the actions, and 1 sample for the reward. So for example, let's say that this 1, 2, 3 is state 1, action 1, reward 1, and then state 2, action 2, and reward 2. Well, what we want is 1 batch for each, 1 batch for state 1 and state 2, 1 other batch for action 1 and action 2, and a 3rd batch for reward 1 and reward 2. That's just the format that is going to be expected next, because then we will wrap these batches into a PyTorch variable. And a PyTorch variable, remember, is a variable that contains both a tensor and a gradient. And that in order to be able to differentiate with respect to a tensor. To be able to differentiate with respect to a tensor, we need the structure of a variable containing a tensor and a gradient. Again, that's how PyTorch works. So to summarize, we're creating 1 batch for each of the states, actions, and rewards, and then we're going to put each of these batches separately into some PyTorch variables, which each one will get a gradient, so that eventually we'll be able to differentiate each of them. Alright, so that's the purpose of this zip function. So let me just remove this comment, and now the only thing that we have to do left is to return the samples. So as I just explained, we cannot return the samples directly for the simple reason that we want to put the samples into a PyTorch variable. So to do this for each of the samples, we're going to use the map function, and this map function will do the mapping from the samples to torch variables that will contain a tensor and a gradient. So as you can see, this map function takes several arguments. The first argument is a function, and this function is going to be the function that will convert the samples into some torch variables. And the second argument is what we want to apply this function onto. So that will be the argument of this function. And therefore, what is it going to be? That's of course going to be the samples. So the second argument here is going to be the samples. But then let's define the function on which we want to apply each of the samples. So to define a function here, we need to first give a name to the function, which we'll call lambda. That's just a name I'm giving. Lambda, then x, which is going to be the variable of this function. So that is just a name I'm giving for the variable. And then colon, and here we give the expression of the function. That is what we want this lambda function to return. And so what it is going to be? Well, it's supposed to be something that will convert our samples into a torch variable. And to do this, we already mentioned it in some previous tutorials. Well, we have the variable function for that. The variable function will make that conversion from a torch tensor to a variable that will contain this tensor and the gradients. So the first thing I'm going to add here is variable. Variable inside of which I'm going to convert x, because x is going to be the samples once lambda will be applied onto the samples. But then that's not all. There is one last technical thing that we need to implement. It is the fact that for each batch which is contained in the sample, for example the batch of the actions, A1, A2, A3 and the other actions, we have to concatenate it with respect to the first dimension, which corresponds to the states. And why do we have to make this concatenation? It's just for everything to be well aligned. That is, that in each row, the state, the action and the reward corresponds to the same time t. So that eventually we get a list of batches all well aligned, and each batch is a PyTorch variable. So how can we make this concatenation? Well, we need to use the cat function from the torch library. So we're going to add here torch, to which we add dot cat applied to x. But then in this cat function we need to specify the dimension with respect to which we want to make that concatenation. And as I just mentioned, this is the first dimension that has index 0. And here we go, we have our function ready. This lambda function will take the samples, concatenate them with respect to the first dimension, and then eventually we convert these tensors into some torch variables that contains both a tensor and a gradient. So that later when we apply stochastic gradient descent, we will be able to differentiate to update the weights. Alright, so this function is ready, and then here as the second argument of the map function, we need to specify onto what we want to apply this lambda function, and that is on all our samples. There we go. We will apply this lambda function on all the samples so that eventually we obtain a list of batches where each batch is a PyTorch variable. Alright, so that was quite technical, but now at least everything will work well. We won't use this technique afterwards, we only use it here, so if you don't want to have a deep understanding of the technical details here, well that's fine, you can just copy these 3 lines of code to sample your memory if you want to make an artificial intelligence with PyTorch. It's as you want, but now the good news is that we are done with this replay memory class. Experience replay is now implemented, and we can move on to the next and final class, which will be the whole deep Q learning model. So in this deep Q learning model, we will have, of course, our network, we will add experience replay, and then all the rest of the deep Q learning algorithm. So it's going to be a much bigger class. We're going to make about 10 functions, but that's only because we're doing this step by step so that you can understand better what's going on. So I can't wait to implement our deep Q learning model, and until then, enjoy AI! Hello and welcome to this Python tutorial. In this tutorial, we are going to make the first step into implementing the deep Q learning model. So basically, we're about to implement the whole process of the deep Q learning algorithm. And so we're going to use what we created before, that is the architecture of the neural network, the replay memory, to integrate this into the whole deep Q learning process. And this whole deep Q learning algorithm is going to fit into one class. So that's the last class we're making to implement our artificial intelligence. And this class will just contain different functions. So we will have the init functions, which will create and initialize all the variables attached to our future deep Q learning objects, which will represent the deep Q learning model itself. And then we'll have some other functions. One of them will of course be to select the right action at each time. We will also have an update function, a score function to get the score and have an idea of how the learning is going, if it's going well, if the exploration is going well, and if it can move on to exploitation. And then we'll have a save function to save the model, that is to save the brain of the car, and then eventually a load function. So we have a couple of functions to make. We're going to make one function for each tutorial, and today we're going to start with the init function, as usual when we're making a class. But first, let's not forget to introduce the class. So we're going to call it DQN for Deep Q Network, then some parentheses, colon, and there we go with our first function. So let's do this. Def, then double underscore, init, double underscore again, and parentheses. So as you understood, in this init function, we are going to introduce the variables attached to our objects. So we're going to have a couple of lines starting all by self, and we will basically create and initialize all the variables that are needed to implement a deep Q network. So we will, for example, create an object of our network, because of course we need our deep neural network. Then we will need our memory. We will create another variable for the memory. So we will have another variable self.memory. But then that's not all. We will have to create as well some variables for the last state, the last action, and the last reward. That's, of course, the variables that you see in the deep Q learning algorithm. And then what else? Well, we will also need an optimizer, to perform stochastic gradient descent, to update the weights according to how much they will contribute to the error when the AI is making a mistake. And then I think that's all. That's basically the variables we now need to create and initialize. But in this init function, we will input a couple of arguments. First, as usual, self, which is the argument referring to our object. Then, since we're going to create an object of the network class, well, since the network class takes as argument in the init function input size and NB action, well, that's the same here. When creating an object of the network class, we will need to choose an input size argument and an NB action argument. Therefore, we can just copy them and paste them here, and here we go. So these arguments will now become also some arguments of the DQN class. Whenever we create some future objects of the DQN class, that is some future deep Q learning models, Well, we will need to specify the input size, which I remind is the number of dimensions in the vectors that are encoding your states, your input states, and a number of actions, which is the number of possible actions the car can make. So I remind these are either go left, go straight, or go right. Okay, perfect. Then we will be creating an object of the replay memory class to create the memory object to get our memory of the transitions. And in the init function we have the capacity argument, but since we will only be using it once, actually when we create the memory, and not anywhere after, well, we won't need to specify a capacity argument. We could do this, but we will directly input the number of transitions we want our memory to have. But then we need one last argument, which is the gamma parameter in the deep Q-learning model. Remember, this gamma parameter is the delay coefficient. That's a parameter of the equation, and therefore we will put it here because we will be using it afterwards several times. So let's put it here. We're going to call it gamma. So far, that is just the name of the argument. And there we go. That's all the arguments we will need for this init function. So that means that whenever we create our deep Q-learning model, that is whenever we create an object of the DQN class, well, we will need to specify as argument the input size, the number of action, and the gamma parameter. And we'll input the real values for them soon. Alright, so now let's go inside the init function. Okay, so now basically this is going to be easy. We are just about to create and initialize all the variables that we'll need. And so let's start with the first one. Let's start with gamma, actually the delay coefficient. So since this is a variable we want to be attached to our object, we start with self. So gamma is going to be a variable of our DQN model. So self.gamma equals the argument that will be input when creating an object of the DQN class. So gamma, and there we go with the second argument. So the second argument is going to be the reward window. So what is this reward window? Well, that's going to be the sliding window of the mean of the last 100 rewards, which we'll use just to evaluate the evolution of the AI performance. We'll have the mean of the reward into this reward window that will slide over time, and what we want to observe is a mean of the last 100 rewards increasing with time. So let's initialize it with self.reward_window. And so since this is going to be a sliding window of the evolving mean of the last 100 rewards, well, we're going to initialize it as an empty list. And then we will append the mean of the rewards over time. Alright, then more exciting, let's create our neural network. So we're going to call it self.model, because basically that's the heart of the model, so I'm calling it model. And this model is going to be nothing else than an object of the network class. And to create such an object, we take our class, network, then parenthesis, and here we just input the arguments of the network class. But we put these arguments in the arguments of the init function, and therefore we just need to copy them right here and just paste them in the network class. And there we go. With this line of code, we create one neural network for our deep Q-learning model. Perfect. Then let's create a memory. So again, we're going to create a new variable that we call self.memory. And again, this is going to be an object of the replay memory class. So let's just take the name of our class. Let's copy it. Let's paste that here. And in some parentheses, we need to input the capacity because the capacity is an argument of the init function. And that's the only argument we need to input here. So what capacity are we going to choose? Remember that corresponds to the number of transitions, the number of events, last state, new state, last action, and last reward. And so, as mentioned in one of the previous tutorials, we're going to take 100,000. 100,000 transitions in the memory. And then we will sample from this memory to get a small number of random transitions. And that's on which the model will learn. Okay, so now we have our memory. Perfect. Now let's get our optimizer. So again, self, we create a new variable that we call optimizer. So optimizer is another variable of our future DQN object. So self.optimizer. And now if we go back up, you can see that we imported torch.optim, which is a module of Torch that contains all the tools to perform stochastic gradient descent. So of course it contains some optimizers, and we gave it the shortcut optim, and therefore here what we're going to do is take the model optim, which is torch.optim, and from this module we're going to take one of the optimizers. So as you can see, they're all listed here. Many of them are excellent. For example, RMSprop is an excellent optimizer that is, for example, highly recommended for recurrent neural networks or unsupervised deep learning. But the other one that is excellent and that we will choose is the Atom optimizer. That's the one. You'll see that with this one, we'll get a good self-driving car. But again, you are totally welcome to try other ones. You can try the RMSprop. But for our model, we will choose Atom. So I'm pressing enter. And in fact, you notice there is the capital A here. That's because we're creating an object of the Atom class. This is a class. But the object will be an Atom optimizer itself. But since this is a class, we need to input some arguments, the arguments of the Atom class. And the arguments are all the parameters that can customize your Atom optimizer. So for example, that's typically the learning rate, the decay, or some other parameters. And besides taking all the parameters of our model, we will specify a learning rate. So speaking of the parameters of our model, we can get them with self.model. So that's the model we created here, self.model, from our network class. So self.model, and then to access the parameters of the model, we add another dot and then parameters with some parentheses. Very simply. So that's just to connect the Atom optimizer to our neural network, the one that we created here. Okay, and then as we just mentioned, we're going to add a learning rate, and the argument for this is LR, and we will set it equal to a value such that the learning doesn't happen too fast. If we get a learning rate too large, then the AI won't learn properly. We want to give our AI some time to explore, learn from its mistakes. You know, when we punish it when it's making some mistakes like going onto some sand or getting too close to a wall, well, we want to give the AI some time to learn. We want the weights of the neural network to update correctly. And so, a good value for the learning rate I ended up with, after trying several of them, is 0.001. Alright, and that's all we need to create an optimizer. So basically, we are creating an object of the Atom class. Great, and then the last three variables we need are the variables composing our transition events. So that's the last state, the last action, and the last reward. And so that's basically what we'll create now. And we will just need to initialize them. So let's start with the last state. The last state, we're going to call it self.last_state. And then how are we going to initialize it? Well, remember, the last state is a vector of 5 dimensions, a vector that is encoding one state of the environment. And as a reminder, these 5 dimensions are the 3 signals of the 3 sensors, left, straight, and right, and orientation and minus orientation. So this is a vector in the intuitive sense, but for PyTorch, it needs to be more than a vector. It actually needs to be a torch tensor. But not only it needs to be a torch tensor, but also it needs to have one more dimension that I like to call a fake dimension that corresponds to the batch. And that's because the last state will be the input of the neural network, but when working with neural networks in general, whether it is with TensorFlow, Keras, or PyTorch, well, the input vectors cannot be a simple vector by itself. It has to be in a batch. The network can only accept batch of input observations. And therefore, not only we will create a tensor for our input state vectors, but also we will create this fake dimension corresponding to the batch. So let's do this, and let's start by initializing a torch tensor. So to do this, there is nothing more simple. We take our torch library, then dot, and then we're going to use the tensor class because, as you might have guessed, this will create an object of the tensor class that is a tensor object. And in this tensor class, we need to input one argument, which will specify the size of your tensor. You can picture a tensor like an array, having one single type, but basically what this will represent now is of course this input state, which you can see as a vector. And so to specify the number of elements this tensor must have, well, we need to use of course the input size, because the input size is exactly the number of dimensions of our input state vectors. Now I should say tensors. And so what we simply need to input in our tensor class to create the tensor object, well, that's input size. And later on, input size will be equal to 5. Alright, so that's good. That's the first thing done. We just initialized a tensor as it should be. But then remember, we need to do another thing. We need to create that fake dimension, because this is what the network will expect for its inputs. And to create this one fake dimension, which by the way has to be the first dimension, you know, the fake dimension corresponding to the batch will be the first dimension of this last state variable. Well, to do this, we simply need to add dot, then unsqueeze, and then in some parentheses, we need to input the index of this fake dimension. And as I just said, this fake dimension has to be the first dimension of the last state. And since indexes in Python start at 0, we need to input 0, so that this new fake dimension is becoming the first dimension. So we have a first dimension corresponding to the batch, and then the dimension corresponding to the tensor, which will contain the 5 elements of your input states. The 3 signals, orientation and minus orientation. And there we go, we initialized our input states properly. Perfect. And then 2 variables to go, and that's going to be much easier because the next variable is the last action. So that's a new variable we're creating for our object, last action. And remember, in the first tutorial of this section, I told you that the actions are going to be either 0, 1, or 2. And then using the action to rotation vector, we will convert these indexes of these actions into the angles of the rotation, which I remind are 0, 20, or minus 20. We can actually refresh our memory with that. Well, it is exactly here. Action to rotation. If the action is 0, well, this will correspond to the first index here, so 0. If the action is 1, this will correspond to the index 1 of this vector, so 20 degrees. And if the action is 2, we will get minus 20 degrees. That's going to be the rotation angle of our car when we play the action. Alright? And therefore, since the action is going to be either 0, 1, or 2, well, the action is therefore a simple number, and so very simply, we can initialize it to 0. We don't need to create any tensor here or anything else. We just need to initialize it with 0. And finally, well, that's the last reward. So self.last reward. There we go. And again, the reward is a float number, which I remind is between -1 and +1. So that's a number again. And as for the action, we will initialize it to 0. And there we go. Congratulations. Our init function is ready. So now we're ready to move on to the exciting stuff. And actually the most important thing for our AI, that's deciding which action to play at each time t. And that's exactly what we're going to do in the next tutorial by creating the select action method. So let's do this in the next tutorial, and until then, enjoy AI. Hello and welcome to this Python tutorial. Alright, so in this tutorial we're going to make the function that will select the right action at each time. So basically we're going to implement the part that will make the car do the right move at each time. That is going left, going straight, or going right to reach the goal and to avoid the obstacles, that is descent. So let's do this right now. We are going to start as usual with a def to define a function, and then we give a name to our function which we're going to call select action. Then some parentheses, and this select action function will take 2 arguments. The first one is self, as usual, to refer to the object, and a second argument, which according to you is going to be which one? Well, what could it be? If you think about it, the action we select comes from the outputs of the neural network, because the outputs of the neural network are the Q values for each of the 3 possible actions, and therefore the action that we play, the action that will be the output of the neural network, depends on the input state. And the input state is exactly the second argument we need for the select action function. It's because we're literally going to take the output of the neural network, and of course the output of the neural network directly depends on the input of the neural network. So that's going to be our argument. And now we can give it any name. We will actually call it state, because the inputs of the neural networks are the input states that are encoded by a vector of 5 dimensions, the 3 signals, orientation and minus orientation. And so now things are going to be easy. We're going to feed the input state into the neural network, the one that we built right above, right here with the network class. And then we're going to get the outputs, which are the Q values for each of the 3 possible actions. And then using a softmax method, which I'm going to explain in this tutorial, we're going to get the final action to play. So let's do this. Let's go into the function and let's implement all this. So the first thing we need to start with is about what I've just mentioned, softmax. The idea of the softmax is that we're going to try to get the best action to play at each time, but at the same time, we will be exploring the different actions. And how can we do that? How can we get the best action to play while still exploring the other actions? Well, we use this idea of softmax, which consists of generating a distribution of probabilities for each of the Q values, Q state action. You know, we have one Q value for each action, go left, go straight, or go right, but this Q value also depends on the input state. That's exactly the Q function you saw in the intuition lectures. This Q function is a function of the state and the action. So since we have here one input state, which is the state here, and 3 possible actions, we have 3 Q values, Q state action 1, Q state action 2, and Q state action 3. And we're going to generate a distribution of probabilities with respect to these 3 Q values. That is, we're going to have one probability for the first Q value, one other probability for the second Q value, and a third probability for the third Q value. And all these 3 probabilities will sum up to 1. And so we're going to do all this with softmax, and softmax will attribute a large probability to the highest Q value. That's why an alternative to softmax is a simple argmax, directly taking the maximum of the Q values, but in that case we're not exploring the other actions. Thanks to these probabilities, we can explore somewhere else using a temperature parameter that we're going to see very quickly. We can still explore them by configuring this temperature parameter. That's why, in general, for deep Q learning, I highly recommend to use a softmax rather than a simple argmax. Alright, so let's implement softmax, and therefore, as you understood, since softmax returns the probabilities of each of the 3 Q values for the 3 possible actions, well, the first variable we're going to create is probs, referring, of course, to these probabilities. So probs equals, and now we're going to take our softmax function. And according to you, where are we going to take it from? Well, of course, remember we imported the torch.nn.functional submodule, which I remind is the module that contains most of the actions to implement a neural network. We gave it the shortcut F, and so that's exactly from this functional submodule that we're going to take our softmax function. But since we gave it the shortcut F, we start here with an F representing functional, from which we take our softmax function. Here it is, that's the first one, and parenthesis. Alright, and now what do we need to input in this softmax function? Well, that's of course the entities for which we want to generate a probability distribution. And what are these entities? Well, these are of course the Q values. So now the question is, how can we get the Q values? Well, of course, the Q values are the output of the neural network. And to get these outputs of the neural network, well, here we go, we need to take our neural network. But in fact, we already have it, because that's what we initialized in the init function. We created self.model, which is nothing else than our neural network, because it is an object of the network class. And so that's perfect. We can just take our model here in softmax, apply this model to the input state, which is the argument here, and that will return the outputs that we're looking for, that is the Q values. And so now your intuition why we had to take the model here to introduce it in the init function might get better. For those of you starting with object-oriented programming, you will see that all this will become natural. So softmax, then, so we take our model, self.model, because this must be the model of the object that we created here. But then we need to get the output of our neural network model, and therefore we're going to add here some parentheses in which we're going to input, well, the input state, named state here. So what we want to do at first is enter state, but now we must be careful to something. State looks like a simple state right now, but remember that state is actually going to be a torch tensor, because later we're going to use this self.lastState to put it as the argument of the select action function. The state argument that is here is actually going to become later this self.lastState. And since this is a torch tensor, well, the model will accept it. So that's fine. But now we can improve the algorithm. So as you understood, state is a torch tensor. And as we said earlier, most of the tensors are wrapped into a variable that will also contain a gradient. So right now what we're going to do first is wrap this input state, that is a tensor, into a torch variable. But since this is the input state, well, there is not going to be some differentiation. We will not be using the gradient of this state torch variable in the computations. And therefore, what we're going to do now is convert this torch tensor state into a torch variable, like so. But then to specify that we don't want the gradient in the graph of all the computations of the NN module, well, we will add here, comma, volatile equals true. So that now we have our state torch tensor into a torch variable, but thanks to this volatile equals true parameter, well, we won't be including the gradient associated to this input state to the graph of all the computations of the NN.module. So that's another technical trick. This will save us some memory, and therefore this will improve the performance. So I highly recommend to do this. And now we're going to add something more fun. It's about this temperature parameter that I've just mentioned. So this temperature parameter is the parameter that will allow us to modulate how the neural network will be sure of which action it should decide to play. So this temperature parameter will be a positive number, and the closer it is to 0, the less sure the neural network will be when playing an action, and the higher this temperature parameter is, the more sure the neural network will be of the action it decides to play. And to add this parameter, I'm going to multiply the output, which are the Q values, by this temperature parameter. So let's start, for example, with 7. And I'm going to specify here the little comment, T equals 7. So that's the temperature parameter that I'm setting equal to 7. We're going to try some other ones, but I just want to start with a small one, because you're going to see that with a small one, our car will still behave like some kind of an insect, but then by increasing this temperature parameter, our car will look more like a car. And besides, the self-driving will be much, much better. And so that makes sense, because the higher is this temperature parameter, the higher will be the probability of the winning Q value. Because for example, if we have softmax of the Q values, let's take some simple numbers, 1, 2, 3. If softmax of 1, 2, 3 equals, for example, 0.04, 0.11, and 0.85, then by increasing the temperature, by taking a higher temperature, right now the temperature equals 1, by taking a higher temperature, like for example 2, so softmax, let's copy this and multiply it by, for example, 2 or 3, softmax of the same Q values but multiplied by this temperature parameter of 3, well, we will get something like 0 for the first Q value, because this had a very low probability, so that's something around 0. Then something very small for the second probability, because this was still a low probability. So let's say, for example, 0.02. But then the third probability, since it was the largest one and a pretty high one, well, by increasing the temperature, this probability will be even larger, because we're going to be even more sure that this is the right Q value corresponding to the action we must play. And therefore, this is going to be something like 0.98. Now, by increasing this temperature parameter, well, we are now even more sure that the third action here should be the action to play, because the probability for the Q value of this action is not only the largest one, but also very high. So that's what this temperature parameter is all about. It's about the certainty of which action we should decide to play. Alright, so I'm going to remove this comment. This was just to explain. And now let's get our action. So how are we going to do that? Well, the principle of the softmax method is not only to generate a probability distribution for each of the Q values, but also, and that's the second step of the softmax method, we take a random draw from this distribution to get our final action. And of course, we will have a high chance to get the action that corresponds to the Q value that has the highest probability, because that's exactly how a distribution works. So there we go. Let's get our action. So we're going to introduce a new variable that we're going to call action. And this action is going to be a random draw of the probability distribution that we just created at this line before. And so how do we get such a random draw? Well, we're going to take our probs, probabilities of each of the Q values. We take probs and then dot, and then we're going to use the multinomial function. And that will give us a random draw from this distribution, probs. So that's all. That will give us the action. Perfect. And now, of course, we are going to return the action. But there is a little trick here. Well, it's the fact that this probs.multinomial returns a PyTorch variable with a fake batch, you know, this fake dimension corresponding to the batch. And therefore, to get the right result that we want, that is the action 0, 1, or 2, we just need to add here data and then some brackets, and the action 0, 1, or 2 that we're looking for is contained in the indexes 0 and 0. Alright, and there we go. Now we have our action. Thanks to this select action function, the AI will now know which action to play at each time. Terrific. So now we can move on to the next function, which will be the learn function, and that's where we will train the whole neural network, you know, with all the forward propagation and then the back propagation using stochastic gradient descent. Well, basically, we will implement the whole training of the deep learning model that is at the heart of our artificial intelligence. So I can't wait to do that. This is going to be an exciting tutorial, and so I'll see you in the next tutorial. Until then, enjoy AI. Hello and welcome to this Python tutorial. Alright, so now in the next function that we're about to implement, we will train the deep neural network that is inside our artificial intelligence. So basically, we're going to do the whole process of forward propagation and then back propagation. So that is, we're going to get our output, we're going to get the target, we will compare the output to the target to compute the loss error, then we're going to back propagate this loss error into the neural network, and using stochastic gradient descent, we will update the weights according to how much they contributed to the loss error. So let's do all this. For those of you coming from the deep learning course, this will be kid stuff, but for the others, don't worry, I'm going to explain that again. So we're going to call this new function learn, and this learn function is going to take several arguments. First, self, of course, which will refer to the object of the DQN class. Then we're going to take our batch state for the current state, then our batch next state, then our batch reward, and finally our batch action. So why do we take this? You probably recognized what is this series. Well, that's of course a transition. A transition of the Markov decision process that is at the base of deep Q learning. And why do we all take them into some batches? Well, that's because, you know, remember, we don't consider the transitions by a series of the tuple current state, next state, current reward, and current action. We created some sample batches here, thanks to the sample function. And so now our transitions are in the form a first batch for the state, a second batch for the next state, a batch for the reward, and a batch for the action. That's the form of our transitions now, and they're all well aligned with respect to time, thanks to this concatenation that we made here with respect to the first dimension. So the point is, now we have these transition of batches, one batch for each of the state, next state, reward, and action, And we do all this because we're using this experience replay trick so that our deep neural network can learn something. Remember, if we only had the transitions by themselves, well, it would be some instant learning, or if you want some very short memory learning, and therefore the model wouldn't learn anything. So we have to take these batches from the memory, which become our transitions, and then eventually we will get the different outputs for each of the states of the input batch state. And we will do this for the batch state and for the batch next state, because we will need both to compute the loss. I will soon remind the balance equation that is at the heart of the deep learning algorithm. So now let's go into the function and let's first get the outputs of the batch state. So I'm going to call this first variable outputs, and then we're going to take, of course, our self.model. So self.model, because we want to get our model outputs of the input states of the batch state. And since our model is actually expecting a batch of input states, well, we can totally input batch state right now for the input of the model. That's exactly how we initialized the states that are going into the network with a torch tensor with this fake dimension for the batch. So that's perfect. We now get the outputs of the model. But then there is another technical trick. If we only do self.model batch state, well, we will get the outputs of all the possible actions, 0, 1, and 2. But that's not what we want. We are only interested in the actions that were chosen, the actions that were decided by the network to play at each time. And so to get these actions we're interested in, that is the actions played, well, we have to use this gather function in which we input 1, because we only want the action that was chosen, and then we add batch action. With this, the 1 and the batch action, we will gather each time the best action to play for each of the input states of the batch state. We only want the action that is played, the action that is chosen. And we get this with this gather, 1, and batch action. But then be careful. The batch state here has this fake dimension corresponding to the batch, and batch action doesn't have it. Batch state has it because we used the onsqueeze here, but we haven't used any onsqueeze for the actions. So we have to add it here so that the batch action has the exact same dimension as the batch state. So we're going to add a dot onsqueeze 0 right here. And actually this is not 0 but 1, because 0 corresponds to the fake dimension of the state and 1 will correspond to the fake dimension of the actions. And finally, the last thing we need to do here is we need to kill this fake batch with a squeeze. And why do we need to do that? Because now we're out of the neural network, we have our outputs, but we don't want them in a batch, we want them in a simple tensor, a simple vector, a vector of outputs. The batch is just when we work in the neural network, because the neural network is expecting the format of tensors into a batch. But now we have our outputs, and in the next balance equation of the deep learning, we won't need them into a batch. So I'm killing the batch here, I'm killing the fake dimension to get back the simple form of our outputs. So I'm just adding here dot and then squeeze. And then, since I want to kill the fake dimension corresponding to the batch of the action, well, since this fake dimension has index 1, I'm adding 1 here. Alright, and now, there we go, we have our outputs. Okay, we have a little warning, what is it? Local variable outputs is assigned but never used. That's okay, we will use it very quickly. So that's our outputs, and now we want to get our next outputs. So now you might be thinking, why do we need the next output? Well, to understand this, we need to go back to the deep learning algorithm, which is right here. That's a part of the LaTeX handbook. So that's the whole deep learning process. At the beginning, we're initializing all the Q values. And then at each time t, well, there we go. We select the action with softmax. That's what we did with the select action function. Then we append the transition. And then, as you can see, we get the prediction, we get the target, and we compute the loss. So why do we need the next outputs as well? That's because of the target. The target is equal to gamma times the next output plus the reward. And we will compute the target right after that. But since we need the next output for the target, let's compute this first. So again, to get the next output, that's very simple. the next output is going to be the result of our neural network when the batch next state is entering it as input. So very simply, we take our model, that is our neural network, and then this time the input of the neural network is going to be the batch next state. The batch next state, but now remember, if we go back to the deep Q-learning algorithm, well, you can see that the next output is the maximum of the Q values for the next state with respect to all the actions. So right now, to get the next output, we need to get the maximum of these Q values. And therefore, I'm going to do here a detach, to detach all the outputs of the model, because we have several states in this batch next states. That's the batch of all the next states in all the transitions taken from the random sample of our memory. So I'm detaching all of them using the detach function, and then I'm taking the max of all these Q values. And since we're taking the maximum of these Q values with respect to the action, well, we have to specify that it is with respect to the action, and since the action is represented by the index 1, well, again, we have to put the index 1 here. And then we have to specify that we're taking the Q values of st plus 1, that is the next state, and the next state is represented by the index 0, because the index 0 corresponds to the state, and therefore here we need to add brackets with the index 0. That way, we get the maximum of the Q values of the next state, represented by the index 0, according to all the actions that are represented by the index 1. And now, perfect, we get our next outputs. These are unused yet, that's why we have the warning, but that's fine, we will use it right now to compute the target. And speaking of the target, that's the next step of this learn function. So there we go, target equals, now let's get back to our AI handbook. The target is equal to the reward plus gamma times the next output. That is the maximum of the Q values of the next state according to the actions. So there we go, let's compute that. So that is equal to self.gamma, and self.gamma was initialized here. It is introduced, so that's a variable of our DQN object. Self.gamma times the next output, as we just said, plus the reward, that is the batch reward. We're working with batches here. So plus batch reward. And that's the target in one sample of the memory. Gamma multiplied by the next output plus the reward. All right, perfect. So now we have our outputs. We also have our target, and therefore we can compute the loss. The loss that is representing the error of the prediction. So let's call this loss TD loss. TD is of course for the temporal difference. That is again at the heart of Q-learning. And this TD loss is going to be equal to the Huber loss. That improves much the Q-learning. That's the loss function we will choose for our artificial intelligence. For those of you coming from the deep learning course, that's really the loss I recommend if you want to implement deep Q-learning. And so how are we going to get this Huber loss? Well, again, we're going to take a function from the functional module, represented by f, and therefore here I'm going to use our functional module, f, dot, and the Huber loss can be obtained thanks to the function smooth L1 loss, that one. So pressing enter, and that's really the best loss function I recommend for deep Q-learning. It really improves the Q-learning. But this is a function, so I'm adding some parentheses. And now there is nothing more simple. The arguments we need to input are the predictions and the targets. So the predictions is of course our outputs, because that's the output of the neural network. The output of the neural network is what the neural network predicts. So that's the prediction. So the first argument here is outputs. And then the second argument is of course the target, the thing we're trying to get. And it's already computed. Perfect. We can directly input target. Perfect. And now we have the loss. Just forgot a little T here. There we go. Now the warning should disappear. Yes, perfect. And now that we have the loss error, we can back propagate this error back into the network to update the weights with stochastic gradient descent. And that's exactly what we're going to do in the next step. So of course now what we have to do, as you might guess, is take our optimizer. our optimizer, which, again, we introduced here. We initialized it, and that's an atom optimizer, which is actually an object of the atom class, and it is already fitted with the parameters of our model, and we already chose a learning rate of 0.1%. So perfect, our optimizer is ready, but now we need to apply it on the loss error to perform stochastic gradient descent and update the weights. So when working with PyTorch, the first thing we need to do is reinitialize it at each iteration of the loop. We must reinitialize the optimizer from one iteration to the other in the loop of the stochastic gradient descent. And to reinitialize it at each iteration of the loop, well, we're going to use the following method, which is 0grad. Here we go. 0grad will reinitialize your optimizer at each iteration of the loop. Then let's not forget the parenthesis. Perfect. And now that it is reinitialized, well, we can perform backward propagation with our optimizer. And how do we do that? Well, we take our TD loss and we are going to backpropagate it back into the network. And to backpropagate it into the network, we need to use the backward function. And inside this backward function, I recommend to input retain underscore variables and set it equal to true. I recommend to do this because this will improve backpropagation. The use of return variables equals true is to free some memory. And we need to free the memory because we're going to go several times on the loss. So that will definitely improve the training performance. And finally, last step of this learn function is to update the weights according to the backpropagation, that is, according to how much the weights contributed to the error. And to do this, we take our optimizer again, which was initialized and reinitialized, and we use the step function. And simply, with this line of code, by using the step function, this will update the weights. That's this line of code that updates the weight. This line of code backpropagates the error into the neural network, and this line of code uses the optimizer to update the weights. And there we go, we have a learning neural network. Alright, so congratulations. This was probably the most technical and difficult part of all this deep Q-learning model. I know PyTorch can be tricky sometimes with these unsqueeze and squeeze, but in the end I promise you will get a very functional neural network and therefore deep Q-learning model and eventually a great artificial intelligence. So now let's move on to the next step of our deep Q-learning model, which will be the update function that will obviously update when the AI will discover the new state. So it will discover the new state and then it will receive the reward depending on the action that it just played and this new state. So we will take care of this with the update function and we'll do this in the next tutorial. Until then, enjoy AI. Hello and welcome to this Python tutorial. Alright, so today we will be making the update function, which will update everything there is to update as soon as the AI reaches a new state. So when it reaches a new state, we need to update the action. The last action becomes the new action that was just played, but also the last state that becomes the new state, and finally the last reward that becomes the new reward we get when we play the action. So that's the logical path that happens right after selecting an action. We need to update all the elements of the transitions. And of course we will get a new transition, so we will have to append this new transition to the memory. And finally, we will also update our reward window, to keep an eye on the evolution of how the training is going, and how the exploration is going. But what's most important for you to understand is that now we can finally make a connection between the AI that we're implementing right now to our map. Because if we go back to our map, remember there is this big update function into the game class, so that's where we're actually making the game with the car and defining how the car should be punished when it's making a mistake. But in this game class, we notice this update function, and in this update function, we notice this line, action equals brain.update last reward, last signal. And actually, this is exactly what we're about to make. We are about to make this update function that will take the last reward and the last signal to get the next action to play. So not only will we update all the different elements of the transition, but mostly we will be playing the action that we should play when getting the last reward and the last signal. And so of course in this update function, we will use the select action function that we just implemented before. We will integrate the select action function in the future update function that we're about to make to select the right action to play besides making all the updates. So that's really important to make this connection with the map right now. What we're about to make is eventually the connection between our AI and the game that we make in this class. And so what we can do now is directly take this update last reward last signal, because that's exactly the function that we will be making with these two arguments here. And just as a quick reminder, brain is our AI object. That is, it's the object of the DQN class. So what we're going to do now is we're going to copy this, update last reward last signal, and that's going to be our next function we're making, and therefore I'm pasting that here. Then just to be careful, I would just like to give some different names than the names we have here. You know, we have last reward here, and I don't want to confuse this last reward with this one. That can be dangerous. So I'm going to replace last reward here by reward. And by the way, same for last signal. Let's just put signal or even new signal to specify that, you know, we want to make the update when reaching a new state and therefore getting a new signal. But then of course, this reward here is going to be the last reward that we get here. You know, when going onto some sand, or worse, getting too close to one edge of the map. That's where we define the last reward. This last reward is going to be the input of the update function, so that's why we have last reward here. But right here, I'm just giving another name for the argument, reward, to not confuse it with last reward here. Alright, so this is the update function, and now let's go inside it, and let's do these two things, that is update all the elements of our transition, and of course, select the action. Okay, so what do we need to update first? Well, as you understood, we want to make the updates when reaching a new state. So the first thing we'll be updating is obviously this new state. That is the new state we're reaching. So I'm going to call this new state, and then equal. And so how can we get this new state? Well, of course, that depends on the signal, the new signal that the sensors just detected. And as a reminder, the state is the signal itself, composed of the three signals of the sensors, signal 1, signal 2, and signal 3, plus orientation and minus orientation. That's our state, so be sure to understand that the signal is the state, but right now it is a simple list of 5 elements. And since this is going to be the input of the neural network, remember we have to convert it into a torch tensor. So that's exactly what we're going to do right now. We are going to take our torch library and then take the tensor class, there we go, which will convert our new signal into a torch tensor. Then it's better to make sure that all the elements of the torch tensor are floats. So I'm going to make a type conversion to convert them into float, like this. And then finally, try to get the reflex of what we need to do next. It's of course to create that fake dimension, to add the dimension corresponding to the batch. And we do this of course with the unsqueeze function, to which we have to input the index of this fake dimension we want to have for the batch, which is 0. Alright, and now we have our new state, composed of the 3 signals of the 3 sensors, plus orientation minus orientation. And of course that will depend on the new signal we're getting with this update function right at this line. Last signal, we get the 3 signals plus orientation minus orientation. And as a reminder, the 3 signals are the density of sand detected around the sensors. Alright, so we just got our new state, so that means we reached the new state, and now we have to make the next update. So according to you, what do we need to update now? What would be the logical thing to update right now after reaching this new state? Well, what we need to update now is the memory. Why is that? It's because at each time t, a transition is composed of the current state, st, the next state, st plus 1, the reward, rt, and the action, at. And right now, we already have st, we already have rt, and we already have at. And we just got the last element of the transition, st plus 1. So by getting this new state st+1, we are getting one brand new transition of the memory. And therefore we have to append this brand new transition to the memory because that's simply our next transition. So that's why we have to update the memory right now. And therefore, what I'm going to do is take my memory object created from the replay memory class, and therefore I'm going to take self.memory to refer to the object. But since I'm using self, I have to include the self in the update function. So now you can really see what this self is for. It's whenever you use one variable that you created and initialized in the init function. So self.memory, and now we need to update it. And according to you, how are we going to update that? Well, the good news is that we already made a function to do that. It's the push function which appends an event or a transition to the memory. So that's exactly what we're going to use now. We're going to use the push function to append our new transition that we just made to the memory. And therefore, here I'm taking not an equal because we're going to use a method, and therefore we can directly use dot push. And first, I'm going to add the transition, this new transition that we just got, and that is first the last state. So self.lastState. So that's st. That's exactly this one. It already exists. Then the next element of this transition is, of course, the new state that we just reached. And therefore, since it is not a variable of the object that we created and initialized in this init function, we don't put a self here. We directly put the new state. Then the next element of the transition is the action. And same, we already have the last action, which is this self.lastAction here. So of course it is equal to 0, but then of course it will be updated with the select action function. But that's this one. So then it is self.lastAction. But now be careful. The elements that we're including in this transition should all be torch tensors. As you can see, that's the case for the last state. It's a torch tensor. The new state is also a torch tensor. And so this must be the same for the action and then the reward, of course. But now you're going to think, how can it be a torch tensor considering that it's simply a number? You know, the action is either 0, 1, or 2. But in fact, that's not a problem. We can still convert this 0, 1, or 2 variable into a torch tensor. This will just be what we call a long tensor. The long is a type, and that's the tensor that will contain an integer, because the last action is an integer. It is 0, 1, or 2. So what we're going to take now is our library torch. Then we're going to take the long, here it is, the long tensor class that will create an object, which will be the long tensor itself. And by taking the self last action function as input, it will create this long tensor object, but it will still contain 0, 1, or 2 into a long tensor object. And that is just to be consistent with the transition that should only contain tensors, because we're working with PyTorch and we're working with a neural network, so we have to work with tensors. So there we go, torch, long tensor, and one last conversion to make. We must be sure that what's inside this long tensor is an integer, and to make sure of it, even if we already know that the last action is 0, 1, or 2, to make sure of it, we're going to make this int type conversion again. We convert our self last action into an integer. There we go, and then we must just put the integer self last action into brackets right here, so that now we get a long tensor of one element, which will be this last action 0, 1, or 2 itself. So the key point is, that's just how you convert a simple number 0, 1, or 2 into a tensor with torch. Alright, and then finally, the last element of the transition, and that's of course the last reward we got. So that's exactly the last reward variable we created in the init function that was initialized to 0, but then of course is updated right here in this code, either when we go onto some send, which is a negative reward, or if we get further away from the goal, that's again a negative reward. If we get closer to the goal, that's a positive reward. And the worst punishment, if we get too close to one edge of the map, well, that's a terrible negative reward, -1, and that's all. So let's add this last element of the transition, self.reward. So I'm copying this, pasting that here, and now we have to make another conversion. which will be of course exactly the same as this one, only since the reward is not an integer but a float number, we will simply make a torch.tensor conversion, but without the int. We will keep the brackets here, because first we have to put the number into a list, and then this list will go as input in the torch tensor class, but we don't have to make that int conversion because last reward is a float number. So what we're going to do is simply add here torch.tensor, then parenthesis, brackets, and we're going to close the bracket here, and we close the parenthesis. There we go. So to summarize, with the new state that we just reached and the reward, we observe a new event of transition that we add to the memory. And this transition contains the last state, st, the new state, st plus 1, the last action played, at, and the last reward, rt. Alright, and now we are good with our memory update. So let's have a quick break and we'll take care of the next update in the next tutorial. Until then, enjoy AI. Hello and welcome to this Python tutorial. Alright, so we just updated the memory after reaching the new state, and now let's take care of the next update. According to you now, what is going to be the next update? Well, basically, we're done with one transition. We updated the last element of the transition, which is the new state. So now it's like we're starting all over again. And when we're starting all over again, well, it's like, we are in this new state of the environment. And so what do we need to do now? Naturally, well, of course, it's to play an action, because we already got the observation of the new state. So now the thing that we have to do is play an action. And therefore, what we need to do now is, of course, use the select action function to play the action. So let's do it. Let's create a new variable action, and let's play the action with the select action function. So I'm taking, well, first self to specify that the select action function is a method of the object of the dequeuing class that will be created. So self.select action. Here we go. Self.select action. And then, of course, since the select action function takes the state as input, because of course the select action function will return the output of the neural network when the current input state entered the neural network. So we have to input the input state here. And since that's the state that we just reached in the environment right now, well, the input state is of course new state, because the state that we just reached at the time we are right now is new state. So in the select action function, I'm inputting new state. All right, so with this line of code, we simply play the new action after reaching the new state. Okay, and now that we played an action, well, we get the reward, and therefore we get a feedback with the reward. And therefore, if we have more than 100 elements in the memory, well, it would be time to learn. And therefore, what we must do now is what logically comes after selecting an action, which is of course to learn. The AI needs to start learning if it is doing the things the right way. And now, since it just played the action, well, we're going to make the AI learn from its actions in the last 100 events. But before we apply this learn function, we have to make this if condition to make sure that we already have reached more than 100 events, because we're learning from the random samples of the memory. We have this huge memory of 10,000 elements. We're taking some random samples of the memory of 100 elements, and the AI is learning from the informations contained in this sample of 100 random transitions. So let's just make this if condition to make sure that the number of elements of the memory, self.memory, and then be careful, just a little trick here, self.memory is the object of the replay memory class, but then the replay memory class has an attribute, which is memory. So in fact, we need to take self.memory.memory. The first memory is the object of the replay memory class, and the second memory is the attribute here, self.memory. So if the number of elements in the memory is, well, we want it to be larger than 100, then colon, and then what happens? Well, we can learn. But before learning, we need to get this random sample of 100 transitions, and this we can get with the sample function, And since the sample function returns the different batches, the states at time t, the states at time t plus 1, the actions at time t, and the rewards at time t, well, what we need to do now is create some new variables, which are going to be the batch of the states at time t, the batch of the next states, the batch of the rewards, and the batch of the actions. And we can simply give the same names as we gave for the arguments here, and paste that here. And these variables will be equal to what the sample function returns, because it returns exactly these batches of the states, next states, rewards, and actions. So what we simply need to do now is get first our memory object, and then from this memory object, we're going to use the sample method, which will take as input, well, the number of transitions we want our AI to learn from, that is 100. That's why we made sure that the memory had more than 100 transitions. So it's going to learn from 100 transitions of the memory. So the learning will be much better. And so now let's make this learning happen. Well, since the learn method is a method of our DQN class, well, we need to access this learn method from the future objects that will be created from the DQN class. And therefore, what we need to take is self. So self refers to that object of the DQN class. And then learn as this learn method. Learn method to which we input, of course, these guys here. The batch state, the batch next state, the batch reward, and the batch action. So these are our batches sampled from our memory. And we get 100 of them. Because we have 100 transitions, and from these 100 transitions, we take 100 states, 100 next states, 100 rewards, and 100 actions. So let's paste that here. And there we go. Now the learning will happen. It will happen from all these random batches. Perfect. And now what we need to do is the very last update. After, reaching a new state and playing an action, well, we got the action to play, but we still didn't update the action. That is our self.lastAction variable. So let's make sure we don't forget this. Let's do it right now. We will update the last action, self.lastAction equals, and of course, action. The action that we just played here with the selectAction function. All right, so now the last action is updated. Then same for the new state. We reached the new state, but we haven't updated the last state yet, because of course the last state was before the state at time t. But since now we reached the new state st plus 1 at time t plus 1, well, the last state becomes this new state here. And therefore we need to update it as well. Self.lastState equals our new state. There we go. And now what do we need to update? Well, there is only one thing left. That's of course the reward. And the reward is exactly the reward we get in reality. So that will be the argument of this update function, which, if we make the connection to our map, will be the last reward, that is, the reward we get right after playing the action in this reached new state. So if we go on to some send, this last reward will be bad, -1. If we get further from the goal, we will get a slightly bad reward, -0.2. If we get closer to the goal, we will get a slightly good reward, 0.1. And if we get too close to one edge of the map, well, that will be a bad punishment. We will get -1 for each edge. So that's the last reward we get in reality. That is the one that happens for real on the map. And this will be the argument of the update function. This last reward here, that's exactly this one. And so since this is the argument of the update function, well, that corresponds to this reward here. And therefore, our self.lastReward variable initialized at the beginning in this init function becomes the new reward we get in reality, that is reward, or that's the same last reward. All right, so now we updated our last reward. And now, since we just got our last reward, well, we can now update the reward window. You remember the reward window we initialized here as one of the variables of the object of our DQN class? That's the window that's going to keep track of how this training is going by taking the average of the last 100 rewards. So, it will be like a sliding window. showing us how the mean of the rewards is evolving. And so since we just got our last reward, well, we can update the reward window. And so how do we update it? Well, we simply need to append this last reward to the window, and therefore what I'm going to do is take my reward window, self.reward window, here it is, and then I'm going to use the append function, and inside the append function we need to input the element we want to append to the reward window, and that's of course the reward. Alright, perfect. And then since this reward window is going to have a fixed size, you know, it's not going to be a growing window, it's going to be a window of fixed size sliding with time to show us the evolution of the reward. And so now we need to decide for a size of this window. And it's simply the number of means of the rewards we will have in this window. And so for example, let's get, you know, the last 1000 means of the last 100 rewards. And so to make sure of it, we're going to add if, then len, then we take our reward window, and we simply add here if the number of elements in the reward window is larger than 1000, well, what we want to do is delete the first element of this reward window, and the first element of this reward window has the index 0. Alright, and now we make sure that this reward window will never get more than 1000 elements, that is 1000 means of the last 100 rewards. That's perfect. This will be a window of fixed size so that we can see if the mean of the rewards is increasing, and therefore if the training is going well, and accordingly if the car does what we want. Perfect. And now one tiny little thing to do left. According to you, what is it going to be? Well, remember, this update function not only updates the different elements of the transition in the reward window, but also it returns the action that was played when reaching this new state. That's why we have in the map action equals brain.update last reward last signal, and therefore it's supposed to return something. And the something it is supposed to return is of course the action. So the simple last thing we need to do here is just return action, the action that was just played when reaching the new state. And that's it. Our update function is ready. It's going to do all the required updates, and it will return the action when reaching the new state. That's perfect. That was the last difficult action to make for all this AI process. Now the rest will be kid stuff. We will just make a score function to return the means of the rewards in the reward window. Then we will make a save function to save the brain of the car whenever you want to quit the application and go back to it. And of course, since you want to be able to load the brain of your car when you get back to it, get back to the application, well, we will end up by making a load function, which will load your model after you saved your model with the save function. So 3 functions to do left, but it's going to be simple, and then we'll have the most exciting section of this first module, that is the demo. We will see if the AI works, we will see if the car reaches the goals, and we will see how we can improve it. And then eventually you will have built your first AI. So I can't wait to start the demo. Let's make these 3 functions first, and until then, enjoy AI. Hello and welcome to this Python tutorial. Alright, so very quick tutorial today to make the score function. And so basically this function will just compute the score on the sliding window of the rewards. And so basically we will very simply compute the mean of all the rewards in the reward window. So this will be very simple. Let's do this now. We're going to make this new function that we're going to call score. And the score function will just take the argument self, because basically we don't need anything. We need to take self because of course we will take self.reward window. So just self, and then colon, and there we go. It's going to take 1 line of code. So we want to compute the mean of all the rewards in the reward window. So that's basically the sum of all the rewards in this reward window that are between -1 and +1, divided by the total number of elements in this window. So let's do this. We're directly going to return that. So I'm starting with return. And so we need to take the sum of all the rewards in the reward window. And to do this, we simply need to take the reward window itself. And so I'm inputting here self.reward window. All right, and so very simply, this will sum all the elements inside reward window. So that's pretty practical. And then to get the mean, we need to divide this sum by the number of elements in the reward window. And to get the number of elements, well, we need to take the len function, and then we take our reward window again. There it is, but now we just need to be careful with something. It's that len self reward window is a denominator, and this must absolutely not be equal to 0. No matter what, we need to avoid this, and to make sure that the denominator here is not equal to 0, we're going to add this safety trick. We're going to add here a +1, so that len self.reward window +1 will never be equal to 0. If the denominator here is equal to 0, this will crash your system. So we must avoid it, and that's totally fine to add a +1. We will still get a good measure of the score. Alright, perfect, and so that's all. We have our score function, which will give us the mean of the rewards in the sliding window. Alright, so now let's move on to the next function, which is the save function that will save your model, that is, save the brain of your car, so that you can then be able to reuse it by loading it with another function that we'll make after the save function. So that's really practical to have this save function to save your models in case you want to reuse them for any kind of purpose where they can be useful. So that's what we'll do in the next tutorial, and until then, enjoy AI. Hello and welcome to this tutorial. Alright, so today we're going to make a function that will save our model, that will save the brain of the car so that we can reuse it whenever we quit the application. Thanks to this save function, we will be able to save the model, then quit the application, and then when we go back to the application, thanks to another function that is the load function, which we'll make after this one, we will be loading the last version of our model that was trained. So that will be very practical, and therefore let's make these two functions, the save function and the load function. So let's start with the save function in this tutorial. So here comes a new def, then save, and then it's going to take one argument that is going to be self. And the reason is that the thing we're going to save is not the whole model here, but our neural network, self.model, and our optimizer, self.optimizer. Because what we want to save is just the last weights that were updated at the last iteration. Because whenever we want to reuse our saved model later, we want it to predict the action to play with the weights that were already trained. So we need to take these last version of the weights, and also we need to take the last version of the optimizer because it is connected to these weights. So let's do this. We have our self, so we'll be able to take our self.model and our self.optimizer, and we will be saving these two objects in a Python dictionary. And to save these two objects, we're going to use the save function from the Torch module. So I'm starting here with torch.save, and in parentheses, we are going to input that dictionary. Brackets. And a dictionary in Python works like that. You have a key, which is your identifier, so that's unique. And for each key, you have the value you want to give to that key. So it's like a mapping function from unique identifiers to a value you want to give for these identifiers. If you take a simple dictionary book, well, the keys would be the words and the values would be the definitions of the words. Well, here that's the same. We're going to make two keys, one key for the first object we want to save, which is self.model, and one second key for the second thing we want to save, that is our self.optimizer. And therefore, let's start with the first key. So we have to give a name to that key, and I'm going to call it state_dict, because then you're going to see that I'm going to use the function stateDict to save our model in the dictionary. So that's our first key. Then to give the value we want to attribute for that first key, well, as you can see, I added a little column here, and here I'm going to add the object I want to save. So the first object I want to save is self.model. So we can just copy this, self.model, and paste it as the value of our first key, self.model. Then we add .state_dict. Here we go, the first one. And then we add some parentheses. And that will save the parameters of your model in this first key, stateDict. And now let's save our optimizer. So we're going to add a second key in the dictionary. And to do this, we add here a comma, then press enter. And there we go with our second key. So the second key, we're going to call it well, we can call it optimizer, then colon, and then we just need to add the name of the object we want to save, and that is self, that is our optimizer. So we add here self.optimizer, and then again, to save the parameters of this optimizer, we add here again .stateDict. And there we go, we have our model saved with all the weights saved and our optimizer saved. Perfect. And then we will save all this into a file. And to do this, I'm going to add a second argument to this save function, which is going to be the name of this file where we want to have our model and our optimizer saved. So remember, I showed you a quick demo in the first section of this first module, self-driving car. You know, that was the demo where we just had some random actions. So that was not yet a self-driving car. But then remember, I clicked on this save button to save the model. And this created the lastbrain.pth file, which is the file that contains the saved version of your model. So I'm going to add here last_brain.pth so that your model and your optimizer will be saved into this created file lastbrain.pth. So you don't have it yet, but as soon as you save your model in the application, this file will be created, thanks to this code we just added. Alright, and so now, perfect, we have a save function that will save your model, save the brain of your car by saving the weights and the optimizer of the neural network that is in fact the brain of the car. So perfect, we now have only one function to create left, that's the load function, and that's because a save function never goes without a load function. You know, there is no purpose saving your model if you cannot load what you save afterwards. So that's the last step in our journey before the exciting demo, and we will make this load function in the last tutorial of this section. So I'll see you in this next tutorial, and until then, enjoy AI!